Next up is laws of motion, which I would say is one of the most important chapters. I mean, if you would ask me, tell me the name of some chapters that you can skip and appear to the exam, and tell me those chapters which you can never skip. I would say the number one, top of the list, would be laws of motion. That's something that you can never ever skip, irrespective of which exam it is. Let it be your NEET exam, let it be the AIEEE, the JEE Mains, the JEE Advanced. You cannot skip this chapter. Such is the relevance and significance of this. Having said so, let's just move on to the topic. Let us not waste time here. So an explosion breaks a rock into three parts in a horizontal plane. Two of them go off at right angles to each other. The first part of mass 1 kilogram moves with a speed of 12 meter per second, and the second part of the mass 2 kilogram moves with a 8 meter per second. If the third part flies off with 4 meter per second speed, then its masses. Okay. So before going through the question here, let us first try to understand what is given to us. See, let's try to picturize this. So there's a condition here, initial condition, the rock was at rest, and then we have a final condition. Okay, so the mass was, so the rock was at rest. Let us call the rock of mass m. At rest means the velocity is equal to 0, right? And then finally what happened is, this rock exploded into three parts, right? This exploded in three parts, and one part out of this, suppose, goes like this. Another part went in the perpendicular direction, and the third one could move in any direction. Now see, one problem with this question is it has not been given that it's going in right angles in which axis. It's only given a horizontal plane, which can be any plane. So what I'll do is I'll assume that this is the xy plane. This is the xy plane. So we have, what we have is one part going like this, other part is going like this, third one is going like this. Okay. So this is part 1, part 2, and part 3. What is the characteristics here? It is m1 v1. Characteristics here is m2 v2, and this has m3 and v3. Now let us try to understand the concept here. Okay, the first part of the question, the concept here, which is that for a system, if the F external acting on it is equal to 0, then it means that the rate of change of linear momentum, I repeat, the rate of change of linear momentum is equal to 0. Okay. Now see, what we need to understand is the primary condition here is that F external should be equal to 0. Now that is where the significance of this first sentence comes. An explosion breaks a rock, right? So it's an explosion, which means this rock being exploded implies that there is no external force acting on it. Explosion is coming from the within, which means it is very safe to assume that F external here is equal to 0. So this is one of the most important concepts here. Students usually don't try to understand this, and they just start solving the numerical, but they don't give emphasis on this. I repeat, explosion comes from forces within the system, right? And that's why we can safely assume that F external is equal to 0. And if F external is equal to 0, what does it imply for the momentum? If F external equal to 0, it implies for the linear momentum, I repeat, for the linear momentum, that the rate of change of linear momentum d by dt of p, rate of change of d by dt of linear momentum of p is equal to 0. What does this imply further? Simple. See, d by dt of 2 is equal to 0. In the same way, d by dx of 4 is also equal to 0. D by dy of 6 is equal to 0. Or in other words, the rate of change of a constant is equal to 0. rate of change of a constant is equal to 0. Now the other way around. If d by dt of p is equal to 0, it overlaps with d by dt of a constant is equal to 0. So if the rate of change of linear momentum is equal to 0, it otherwise means that the linear momentum is a constant. Therefore, I can say that linear momentum is a constant. Excuse me. So when you have linear momentum as a constant, it implies that momentum initial should be equal to momentum final. Or in other words, momentum before explosion should be equal to momentum after explosion. I hope that makes sense, right? Okay. In this case, what is momentum before explosion? See, that would be mass of the rock, big rock, into velocity. What is momentum after explosion? We have three parts here, right? So I'll write it like this. Momentum vector 1 plus momentum vector 2 plus momentum vector 3. Okay. Now assuming this to be in the xy plane. See, this is where the vector approach becomes really important in this question. So say drawing the xy axis for our reference, okay? So this is positive x, this is negative x, this is positive y, and this is negative y. So when we say that the first vector and the second vector are mutually perpendicular, I can assume that it's like this, and the second vector would be like this, right? Because they are perpendicular to each other. And if I write that, can I mention this as vector p1 and this as vector p2? And we don't know where is vector p3 located. Okay, we don't know the angle. We don't know which coordinate it is. It can be like this. It can be like this as well. It can be in any direction. Let us assume that it's going like this. Now, what is this vector v? It is at rest, so that is 0 into. What is p1? P1 is actually m into vector v1 plus. What is p2? It is m into vector v2. What is p3? It is m into vector v3, right? Now, what is p1? M into 0 is 0. The first mass is given us to be, first part of mass 1 kilogram, right? So this is 1 kilogram moving at, 1 kilogram is moving at 12 meter per second. The other is 2 kilogram is moving at 8 meter per second. So I can write here 1 kilogram moving at 12 meter per second, which is 12, of course, but most importantly, this should be j cap, right? Plus ms, sorry, m1 and m2, right? Okay, and m3 here. So m2 is 2 kilogram into 8 meter per second. Along which direction? This would be along the positive I cap direction. Plus, do we know m3? We don't know m3. So this is m3 into v3, right? Now, so this takes us to 0 is equal to 12 j cap plus 16 I cap plus m3 into vector v3. Okay. So if I write this one more step, what is m3 into vector v3 is equal to? M3 into vector v3 is equal to minus 12 j cap minus 16 I cap, right? Now I'll take magnitude on both sides. Magnitude on both sides. So what do we get? This would become m3 into magnitude of vector v3. I repeat, m3 into magnitude of vector v3 is equal to magnitude of minus 12 minus 16, which actually is equal to root of 12 square plus 16 square. Now, What is magnitude of velocity? Magnitude of velocity is actually nothing but speed, right? Magnitude of velocity is nothing but speed of 3. So we have speed of 3 is equal to root of 12 square plus root of 12 square plus 16 square, which is nothing but root of, so we have 144 plus 169, right? Sorry, 16 it is, so it is 256. 10, 5 plus 5 is 10, so it's 400. So it's root of 400, which is equal to 20. So we have m3 into, what is speed of 3? It is given directly in the question that the third part flies off with a 4 meter per second speed. So it is 4 is equal to 20, and therefore m3 is equal to 5. So let us go to the question once again. What is the concept? The concept is that if f external is equal to 0, then it implies that the rate of change of momentum, which momentum? Linear momentum is equal to 0. And what does it imply? It further implies that the momentum should be a constant. And what is that gives us in turn? If the momentum is constant, it implies that momentum before explosion should be equal to momentum after explosion. And then we have the vector approach. And see, you can also confirm one thing from here, that the vector v3 is having both minus j and minus I, which means it should be in the third quadrant. So this assumption is actually correct. Okay, right. So we can also figure out one more thing here. If we were to take this resultant here, resultant of 1 and 2, what we get is root of p1 square plus p2 square. So if you see that the resultant of 1 and 2 is actually balanced with the third momentum vector, right? So that's also one concept that you can derive it from here. So we've done the explanation of the concept, we've done the numerical, and we've also done the analysis of the result. Right, so that's it. Let us move on to the next question. The upper half of an inclined plane of inclination theta is perfectly smooth while the lower half is rough. A block starting from the rest at the top of the plane will again come to rest at the bottom if the coefficient of the friction between the block and the lower half of the plane is given by. So first, let us try to visualize the given scenario here. So say this is the inclined plane, okay? This is the inclined plane, and the lower half is rough, right? The lower half is rough, okay. So say this is the rough surface, and the upper half is smooth. So this much region is smooth, no friction here. Okay, so this is the primary thing given in the question. So there is coefficient of friction mu here, and here mu is 0. It is smooth. And what else do we have? A block is starting from rest, right? So say there was a block here, right? A block here like this. Now what is happening to this block? See, this block will slowly slide like this. It will go easily through the, I repeat, it will smoothly slide like this. It will smoothly slide like this, and from here it will experience friction. It will here experience friction, and then the speed will reduce, and eventually it will come down and be at rest. Okay, so this is the condition given to us. Let us try to visualize this once again. So let me call this point as A, this point as B, and the last one as C. So let us try to imagine the condition once again. Okay, so the object was kept at A, right? It is smooth, which means from A to B, the body will slide down smoothly. And then B to C, what happens is it will experience some friction, and the movement will actually be retarded, and eventually it will come to rest. Okay, so from A, smooth movement slide down, and from B, it will experience friction and it will slow down gradually and approach zero velocity. Okay, so this is given to us. So what we'll do is we'll try to figure out this question in a very detailed way, considering both travels from A to B and from B to C. But before we do that, something students often ask me as a doubt is the resolution of weight is the resolution of weight on an inclined surface. See, this is one such idea where if you don't give much emphasis on the logical reasoning behind this, what makes this, or rather, what is the primary reason which causes this inclination to resolve, if that idea is not there, you'll find it really difficult to do questions, especially at the JEE mains level. Well, not to underestimate NEET, and definitely this question is from 2013 NEET, the very first time NEET was launched. So these kind of concepts are really important. So we'll try to understand that concept first, resolution of weight in an inclined plane, and then come back to this question. Okay. So, okay, let me take a different board now. Okay, so let us discuss about resolution of weight where on a inclined plane. See, I can assure you, if you pay much attention here, like if you put your maximum focus here, this explanation will help you to understand any resolution when it comes to the inclined plane. Okay, I'll try to make it as simple as possible and as well. Of course, see, when I say simple, it may take some time. So the length of the explanation will definitely be more, but it will be as clear as possible from my end. Okay, let's see. So first, what we need to understand is, if there's a surface here, right? If there's a surface, and if there is a block placed on it, same mass m. If I were to draw a free body diagram, I repeat, if I were to draw a free body diagram of this block, what would I do? See, the first thing you need to understand is, what is free body diagram? It is a diagram which represents all the forces acting on the object of interest. So to get this idea clear, what we'll do is, we'll consider two objects of interest here. Which all are they? One being the mass and the other being the surface. Once this idea is clear, you have the foundation to understand what happens in an inclined plane. Okay, so let us try to pay maximum attention here. See, what are the forces acting on the weight m? We know that any object will experience a weight which is experienced towards the center of the earth, right? The earth will pull every object towards the center of it. We know that. Now, see, normal reaction is one such region where students often get confused by the statement. Normal reaction is an action-reaction pair. Okay. It's an action-reaction. People ask me, which one do we take? Do we take the action or do we take the reaction? So that's where the doubt comes in. Let me clarify this. See, what we need to understand is, when an object is kept on the surface, I repeat, when an object is kept on the surface, what happens is, the object will exert a reaction, okay, which we call as the normal. Why do we call this normal? It assumes normal because it is perpendicular to the surface. So in geometry, anything which is perpendicular to the surface, we call that as normal, right? So that's how the terminology comes in, normal to the plane, normal. So there's a normal reaction which is acting on the surface. Okay, so this is acting on the surface and it is acting due to the mass m. Okay, so what is NSM? It is a normal reaction acting on the surface. Okay, now, by Newton's third law of motion, we know that if there is an force acting, there would be equivalent opposite force acting. Now this time this would be on the block and not on the surface. So the block will experience a reaction pair, say N, this time on M due to S. Okay. So I repeat that once again. So normal reaction acting on mass due to S, equivalent opposite normal reaction acting on the surface due to the mass. Okay, now let us try to understand the free body diagram. See, when we say the free body diagram, if the object of interest is mass, if the object of interest is the mass, how many forces are acting here? There are only two forces acting. One is the weight of the body acting downwards, and the other one is normal reaction on the mass due to the surface S. Right? We don't include the third force here. Why? Because the object of interest here is mass and not the surface. But if we were to ask if we were to ask to draw the free body diagram of the surface, how will it look like? It will look like this. And force acting on the surface. Which one is this? The normal reaction acting on the surface. Due to which the object present, due to the mass, to the block present here. Okay, so we won't see the other two pairs here, other two forces here. Okay, so those who are watching it offline, online, please make sure that you pause the video here, you go through this entire explanation one more time, and then move to the next one. Anyway, I'll repeat it one time. See, a block of mass m is kept. It is kept on a surface. It will be pulled down by the gravitation towards the center of the earth, resulting in the force mg. A normal reaction acting on the mass due to the surface. Equivalent opposite, Newton's third law. Normal reaction acting on the surface due to the mass. Acting on surface, opposite and equal, acting on mass. Okay. Free body diagram, what is it? All the forces acting on the object of interest. If the object of interest is the mass, okay, I think it should be block, right? If the object of interest is the block, then what do we have here? There are two components. One is the weight, which is acting downwards, and the other is the normal reaction acting on the block due to the surface acting upwards. And when we consider the surface, how many forces are acting? There is only one force which is acting on the surface. Okay, so this is the concept behind the free body diagram and the forces acting on a block. Okay, now having said this, let us now try to understand what happens in a inclined plane. Okay, see, before we go to that point, let me add something more here. See, if you give more normal reaction here from the surface, what will happen? If this normal reaction is more than the weight, what will happen? The body will say, for example, the body is pushed upwards from the ground, right? If the normal reaction is less and if the weight is more, what will happen? The body will show the tendency to come down from the surface. If the normal reaction is equal to the weight, the body will stay there on the surface. Okay, so what I want to imagine is, imagine a piece of cake and there is a coin present on the top of it. So if the normal reaction is more than the weight, more than the weight, what will happen is the coin will get tossed upward, leaving the surface of the cake. Okay, if the weight is more, what will happen is the normal reaction is overcome with the weight and the coin would press towards the inner surface of the cake. And if both forces are balanced, then the coin will stay. It will stay on the surface of the cake. Okay, that was a bad example, but I couldn't come up with another one so instantaneously. So that's try to visualize that concept. Okay, right. So okay, if you want to have further explanations, we can maybe discuss after the class. Those who are watching it online, if you want to have further discussion for the examples, please do write in the comment box. I'll try to come up with a variation of forces there. Okay, now let's see what happens in the inclined plane. Okay, so okay, I mean you have to need a couple of diagrams to draw this. Okay, so let's say we have an inclined plane here. Okay, this is an inclined plane, and this angle is theta. This is 90 degree. So how much is this angle? This is 90 minus theta, right? Okay, let me name these points also. So we have A, B, and C. This is the block of mass m. Block of mass m. So if this is a block of mass m, let us try to find out the normal reaction. Oh, sorry, to try to find out the various forces acting on it. So we know that for any body kept on a surface, there will be two forces acting on it. Number one would be the weight, and number two would be the normal reaction, right? Normal reaction, which is acting perpendicular to the surface. Now, which surface? Perpendicular to the surface of contact, actually. Perpendicular to the surface of contact. So, which is the perpendicular surface of contact here? It is AC and not AB. It's very important. AC is the point where the object is in contact, right? So, normal force would be acting perpendicular to the, normal reaction would be acting perpendicular to the surface of contact, which is AC here. Okay. Now let us try to understand the resolution part. So one more time, we have a inclined plane, right? The object is kept here. So say the weight originates from the center of the body, and the weight is acting downwards like this. Okay. So what is this force? This force is mg. Now we'll have to resolve mg. Okay. Now how do we resolve mg? See, for that we need to first find out the angle which it is making with the, okay, let us keep that angle, let us discuss that in a separate video. So what we'll do is we'll try to resolve this force mg into two components. Okay, into two components, one which is parallel to the surface and the other which is perpendicular to the surface. Let me write it down first. So we will resolve mg into two components. Okay, one which is parallel to the inclined surface, one which is parallel to the inclined surface, and the other which is perpendicular to the inclined. See, we are taking longer than usual to complete a problem. See, those students who are here for the maybe the second or third revision, excuse me, this might be very elementary for you, but those who are here for the first time, and the students who are listening to the recorded sessions online, see, this is going to be a bit lengthy, but please try to focus your attention towards the explanation. Things will become very logical and things will become very clear to you, and I bet you'll be able to resolve any component here, and try to visualize what happens in the resolution. Okay, so parallel to the inclined surface, and one component will be perpendicular to the inclined surface, and this parallel to the inclined surface, we'll call that as the horizontal component. Horizontal component of weight. Horizontal component of weight, and the perpendicular to the inclined surface, we'll call that as the vertical component of weight. Okay, so say let this be W is equal to mg. Okay, so the horizontal component, for our ease of understanding, I'll write it as wx, and the vertical component, I'll write it as wy. Okay, so I'm going to solve it like this. One component perpendicular to the inclined surface. Okay, so we only have perpendicular to the inclined surface like this, right? And another component like this, which is parallel to the inclined surface. Okay, now I'll have to redraw this diagram, or maybe a couple of times at least. So I'm trying to take your attention towards this concept resolution again. Okay, so let's see. So this is the ground, the inclined surface. The inclined surface is AC. Now I'm going to draw only the forces. Okay, so the weight was acting downwards like this, right? This is mg. This is W is equal to mg. What do we need? One force which is acting perpendicular to the surface. So this is the inclined surface is AC, right? The inclined surface is AC. So the one which is inclined surface is AC. The one which is vertical component is WY, which means this vector here represents WY, right? What do we have next? Horizontal component. Horizontal to what? Horizontal means parallel to the inclined surface. What's the inclined surface? The inclined surface is AC. So we need one vector starting from this origin, which will be parallel to AC. Let us draw it here. So this is the next vector, and what do we call this as? We'll call it as Wx, right? The vertical component is Wy, and the horizontal component is Wx. Okay. Okay, so we have resolved this. Right, now see, being a vector, being all of these being vectors, what can we do is, we ideally can, okay, wait, what we can do is, let us, see, considering this case here, okay, considering this case here, if I do understand this, suppose, say this is Wx, okay, this is Wx, and see, we know by the basics of vectors that this vector, if it is displaced from its initial position, it doesn't affect the, it doesn't, you can keep this vector anywhere in this plane and it doesn't affect the properties of the vector, which means if this vector is kept here, it acts as Wx, it doesn't matter where it is kept. So I'll take this Wx and keep it in such a way that it starts from the origin of this vector and it ends at the terminal end of the last vector. Okay, I repeat, this is Wx vector, it can be kept anywhere on the surface, but I'll keep it in such a way that it looks like this. Okay, like this. Now, okay, like this. Now let me, okay, now we'll try to visualize this one more time. Okay, so we have the fixed surface, here, this is fixed, then we have theta to be the angle of inclination, this was A, B and C, right? And then we had one force acting perpendicular like this, right, which is the main component mg. Then we have the inclined, the perpendicular force or the component, which what we call as wy, right? And then we have the wx component here, right? Now what we need here is to find out this angle theta, sorry, this angle, this component, this angle here. To find out that, what I'm going to do is, I'm going to draw, okay, let me label these as well. So let us say this is D, E, F. Okay. Now see, to find out that angle, what I'm going to do is, I'm going to draw only a couple of points here. So D, E, F, maybe this is E, F, right? So this is G and H. Okay. So please try to pay attention here. I'm going to draw only certain lines here. So this is T, this is H. Okay. Goes like this, comes like this. So this is T, H. What do we have here? This is G, right? G and C. And this is B. See, one thing we know from basics of geometry is that DH is parallel to CB, right? Which means these two are alternate interior angles, right? So if this angle of inclination was theta, this is 90 degree. By triangle sum property, this is 90 minus theta, and being opposite alternate interior angles, this angle will also be equal to 90 minus theta, right? Now this component, the wy component, being the vertical component, this would be inclined at 90 degree to the surface, which means this angle here is 90 degree, right? So if this is 90 minus theta, then the only possible value for this angle is theta. Okay. Uh, Please try to rewatch that. It's very basics of geometry. So we got these two components here, right? And now, if I had to draw the final diagram one more time, so we have the fixed surface here, fixed surface, right? A block W is kept, sorry, a block of mass M is kept. Weight is acting downwards. We have a vertical component and we have a horizontal component. The horizontal component is, vertical component is Wy and the horizontal component is Wx, and this angle is theta. Okay, so the triangle was triangle DHG with 90 degree here. So now again a doubt which most of the students not from the mathematics background always ask me is how to understand this Wx and Wy. Let us take that point also here. So so it is DGH, right? Now guys, tell me if this is 90 degree, tell me, and now tell me what is, okay, say if this angle is theta here, if this angle is theta here, tell me what is sine theta from here. Sine theta is opposite by hypotenuse, right? Opposite is HG, by the hypotenuse is DH. Similarly, tell me what would be cos theta, would be adjacent side being the closest one to this. So adjacent side is DG, the whole upon hypotenuse is TH, right? Now tell me what is HG from here. So HG is equal to DH into sine theta. And what is DG from here? DG is equal to DH into cos theta, right? So let me rewrite these two here. So HG is equal to DH sine theta and DG is equal to DH cos theta. Now let us try to bring these variables here. So what is HG? See from the figure, what is HG? HG is Wx, right? HG is Wx. So let us write it first. So Wx is equal to, what is DH? DH represents mg, right? So Wx is equal to mg into sine theta. That is our first important point. Wx is equal to mg into sine theta. And what is dg is equal to? Dg is equal to, let us look at it, dg is equal to wy, right? So dg is equal to wy, which is equal to, what is dh from the figure? Dh from the figure is mg. Dh from the figure is mg. So we'll write down here is equal to mg into cos theta, right? So two important derivations. One, that Wy is equal to mg cos theta, and the horizontal component being Wx is equal to mg sin theta. Okay, now if we come back to the question here, we were actually discussing about the horizontal component and the vertical component, right? So what is the horizontal component? Wx is equal to, if you write this, that becomes Wx is equal to W or mg sin theta, and the vertical component being mg cos theta. Okay, now see, this is taking really longer than usual, but as I always say, every problem is explained in such detail wherever it's required to address that student who is doing it for the first time. This goes for the online and the offline students as well, who's watching for the first time and who has who feels that his basics needs to be corrected from the very beginning. Is the reason why we are addressing every problem in this detail. Okay, sorry that I'm making the explanation really lengthy. Okay, so that was it. So we discussed about the resolution of the weight, right? So now let us come back to the figure one more time. So if this is the fixed surface, right? This is the fixed surface. If there is a block placed like this, the weight acting towards center of the earth, mg cos theta is the perpendicular component and mg sin theta is the horizontal component, right? Now let me tell you the mm, the concept of why this is important. See, so this is the normal reaction, right? This is normal reaction here. See, what I want you to do is I want you to visualize that, say for example, this theta is equal to 60 degrees. Okay, let us reduce this theta, maybe to this. We still have the block here, right? We still have the block here. Now, the normal reaction would act like this, right? So the sine theta component here, weight is acting downwards. The cos theta component here, this is mg cos theta. This is mg sine theta, right? So maybe theta is 30 degrees. Let me try to even reduce theta. So maybe like this, small inclination. Now what do we see? The block is over here. Weight is almost perpendicular, right? This value is really small, mg sine theta. Mg cos theta is even smaller. Okay? And normal reaction acts like this. Would be definitely inclined at some point like this, right? And then if you were to make this theta almost equal to 0 degrees, there is no inclination, right? Two surfaces overlap, right? We know that force, the vector can still now be resolved. Now what are the components? It is mg sine theta, right? And mg cos theta. Now as theta is tends to 0, what is sine theta? Sine theta component is mg into 0, it is 0. So the horizontal component which was present earlier now disappears. Okay, so see, this was the horizontal component mg sine theta, it got shortened here. So as the theta value decreased, the mg sine theta component decreased, and as the theta value was really small, the mg sine theta component was even smaller, and when the theta was almost equal to 0, mg sine theta disappeared, which means this component of weight is no longer present here, right? It's only the mg component. Let us see what happened to mg cos theta here. So this would be mg into, what is cos theta? Cos theta is cos 0, which is 1. So the only component what we get is mg, and the normal reaction would balance this force. Excuse me. So that is the concept regarding resolution of weight. Okay. Okay. Now I think we can come back to solving this question. Okay. Okay. Now let us come back to solve this question now. Oh, I think the question would span a really long time. Okay. So the upper half of an inclined plane is perfectly smooth while the lower. Okay. Now, as we said earlier, we will discuss this question in two parts. One will be the upper part, travel from A to B, and the next would be travel from B to C. Okay. So let us write it down first. Travel of the body from what? From A to travel of the body from A to B. Okay. So this is the body here. This is the fixed plane. This is the fixed plane. Inclined body. The angle is theta. The object is kept here. We are talking only about the smooth plane. Okay. So we now know that this vector here is mg sine theta, right? We have another vector here which is mg cos theta. Normal reaction acting perpendicular to the point of the contact surface, and right, these are the forces acting on it. Now what we'll do is we will try to understand the forces acting on it. See, this object is in motion, right? This object is in motion. And when an object is in motion, we know that the net force acting on the body would be actually equal to mass into the net force, net acceleration acting on it. What is the meaning of F net and A net? Pretty simple. F net means the sum of the components along Fx and Fy. A net means the sum of, sorry, my bad, resultant of the components Ax and Ay. So what is F net? F net is equal to root of Fx square plus Fy square. Similarly, what is A net? A net is equal to root of Ax square plus Ay square. Okay. So this is something we need to understand. Now let us see what are the forces acting on the body here. See, this is the object present here. The vertical component is n here, right? Acting upwards, and the other acting downward is mg cos theta. So if we were to write down Fy, right? If we write down sigma Fy, what do we have sigma Fy as? Sigma Fy would be n minus mg cos theta. Okay. Well, what would be sigma Fx? Sigma Fx would be, see, the only force acting here is mg sine theta acting downwards, right? Mg sine theta acting downwards. So it is mg sine theta. Now, what is Ay? So if you look at Ay, the object is actually sliding downwards, right? The object is sliding downwards and it is not having any motion in the vertical direction. I repeat, say if you consider this block here, if you consider this block, okay, now I'm not able to select this block. Okay, so this block is sliding down to the inclined plane. It is not going up like this. It's not going up like this. It's not going down like this. It is rather sliding down the surface, which means there is no motion in the vertical direction, which means there is no motion in the vertical direction, either in the positive vertical direction or in the vertical direction or negative vertical direction. It is having motion only in the inclined plane, which means along the vertical plane there is no vertical motion, right? So if there is no vertical motion along the if there is no motion in the vertical plane, what can we write for Ay? We can write that Ay is equal to 0, right? And what would be Ax? There would be any component, say there would be a component present called as Ax, right? Now if Ay is equal to 0, what is sigma Fy is equal to? It would be m into Ay, which is equal to m into 0, 0. But what is sigma Ax? What would be sigma Fx is equal to? We know sigma Fx will be equal to m into Ax, which is equal to, what is m into Ax? The value of Ax is mg sine theta, right? M into g into sine theta. Okay. So let us consider only this two part of the equation. So we have m into Ax is equal to m into g into sine theta. If you cancel m on both sides, what do you get? What you get is Ax is equal to g sine theta, right? So what we get is Ax is equal to g excuse me. What we get is Ax is equal to g sine theta. Okay. Now, if Ax is equal to g sine theta, let us try to understand the question with even more detail. If Ax is equal to g sine theta, what is A net is equal to? It is equal to root of Ay square. What is Ay square? It is 0. So it is 0 square plus, what is Ax square? Okay, let me write it as Ax square. So A net is equal to root of Ax square, or otherwise A net is equal to Ax, and therefore we can say that A net is equal to g into sine theta. Okay. Now let us try to understand the motion from A to B. So this is A till B, right? So from A to B, guys, let us not try to pull out the equations of motion in a straight line. So what is equation of motion? So it is v square minus u square is equal to 2 into A into S. Is there any vertical motion here? No. which means we have only the horizontal motion. So it is Vx square minus Ux square is equal to 2 into Ax into S, right? Now, since the object is starting from rest, since the object is starting from rest, we can say that ux is equal to 0, right? Since it is starting from rest, ux is equal to 0, which means vx square minus 0 is equal to 2 into, instead of ax, what do we have here? We have derived ax is equal to g sine theta. So into g sine theta into, see, since it's the lower half, since it's the upper half, we know that the upper half here is L by 2, right? So this is L by 2. So what do we get? What we get is Vx square is equal to 2 by 2 is 1, g into sine theta into L, right? So what we get is Vx square is g sine theta into L. Okay. Are we done with the question? No. What we need to find out is, the next is, now we have discussed travel from A to B, right? Now what we'll discuss is travel from B to C. So let us do that part also. So we just derived that Vx, which is actually velocity in the horizontal direction at point B, is actually equal to, what is the value? G sine theta into L, right? So the value is G into sine theta into L. Yes, I do understand. Now you may need the diagram one more time. No issues. We'll draw it. So fixed plane, inclined plane, theta. This is the rough plane, right? The object is now here. Now what is the velocity possessed by this object? It is, velocity is Vx, or let us say it is velocity is Vb, and the object is coming downwards, right? And the object is coming downwards. Okay. And it eventually reaches C. And what is the velocity here? Velocity at C is actually equal to 0. See, so velocity at B will actually now become the initial velocity at the point B. I repeat, the velocity at which the body was covering the smooth plane, will now become the initial velocity for the rest of the motion. Okay. So we have initial velocity at UB is equal to G into sine theta into L. What is the final velocity? The final velocity is at C, which is equal to 0, because the question says that it comes to rest. So I can otherwise write that U is equal to G sine theta into L, and I can write that V is equal to 0. Okay. Now comes the interesting part, which is the resolution of the forces. Let us see that also. So we have the body here. Now see, since there is, okay, let us not skip that. So normal reaction acting perpendicular to the contact of surface. The weight acting downwards is mg cos theta. We know that the horizontal direction force is mg sine theta. And what will act, see, since the object is moving, since the net acceleration is towards downwards direction, Fk, which is force of kinetic friction, but kinetic friction would be acting in the direction which is opposite to the motion. So opposite to the direction is towards this, which means opposite to the motion, diametrically opposite would be moving in the upward direction. Sliding downwards is the direction of motion. Sliding upwards would be the direction of motion of kinetic friction, Fk, right? Okay. Now, what is Fk? See, we know that Fk is nothing but mu into n, right? Fk is mu into n. Okay. Now what is n? N is mu into n, or sorry, n is mg cos theta, right? So, okay, wait, what is that we're trying to find out here? We're trying to find out the next equation. Okay, so the next equation for the motion from B to C, for the motion along B to C, we have V square minus u square is equal to 2 into a into s, right? 2 into a into s. But this is vx, ux, and ax. Okay. Now let us see for the along the horizontal direction. Along the horizontal direction, there is only two forces acting: mg sine theta and fk. What is fk? Mu mg cos theta. So, if we were to analyze this further, for the motion along x direction, what is sigma fx is equal to? Sigma fx is equal to m into ax, right? Now, how many forces are acting along x direction? One is acting downwards, mg sine theta, and the other is acting sliding upwards, which is mu mg cos theta. See, what is the net direction of motion? The direction of motion is towards the sliding downwards. So whatever is coming downwards, we'll take it as positive, and whatever is sliding upwards, we're taking as negative, which means sigma fx here would be mg sine theta minus mu mg cos theta is equal to m into ax. Okay. So we'll cancel m here. So what we get is g sine theta minus mu into cos theta is equal to ax. Right. This is the derivation we have here now. Okay. Now if we have ax here, can we come back to this equation? Vx square minus ux square is equal to? Yes, let's try doing that. So what is Vx? It is final velocity 0. So we have 0 minus, what is Ux? The initial velocity, which is g u square, right? So we have g square. Wait. There's a mistake here, right? It's not Vx, it is Vx square. So it is Vx square, it is ub square, so it is u square. My bad. So it's not g square, it is u square, right? So ux square we derived it to be ux square we derived it to be sine theta into g into l. So we have g into l into sine theta is equal to 2ax. 2 into what is the value of ax? We have it here, which is g sine theta minus mu cos theta into L. Into S, right? 2as. What is S? S again is half of the moving length. So S here is L by 2. Okay, S here is L by 2. So let us try to multiply this. So 2 by 2 is 1, right? 2 by 2 is 1. So what we get is minus GL sine theta is equal to G sine theta minus mu cos theta. So if you take g's to the other side, what you get is minus 2gl sine theta. No, there is one L component here. I missed that. Sorry, this whole is into L, right? And this whole is into L. So we have L sine theta, L cos theta would be equal to minus mu cos theta into L, right? And now what will happen? Simple. L by L is 1. So what do we have rest? 2. Okay, minus and minus becomes positive. 2 sine theta is equal to mu cos theta. And therefore what is mu is equal to? Mu is equal to sine theta upon cos theta, which is equal to tan theta. Okay, 2 is here, right? So mu will be equal to 2 sine theta. So 2 tan theta. And therefore what we get is the correct option is mu is equal to 2 tan theta. Okay. See, it's a really long derivation. Well, actually, we do understand that it's not possible to watch such a really lengthy explanation. But the reason why I took it, as I say that in every video, it's to make sure that you understand the concept behind every question. So just imagine the kind of concepts that are asked in one question. It covers friction, it covers resolution of weight, it covers your concepts of resolving forces on an inclined plane, it covers your concept of application of equations in a straight line, it covers interlinking all these, right? So it's a really good question. And see, when you do this for your exam, right, when you do this for exam, things are really simple, because you know that for the force acting is g sine theta. When there is frictional law, it is g sine theta minus mu cos theta. So you have ready-made answers with you. But as I said, these lectures are designed for those students as well who cannot or rather who need more and more detailing in the concepts. Okay, so I would like to apologize one more time for this lengthy video. Sorry, students. So okay, having said that, let's move on to the next question. Three blocks with masses m, 2m, and 3m are connected by strings as shown in the figure. 3m, 2m, 3m. Upward force F, constant speed V. What is the net force? See, the direct answer is, the moment you see it has constant speed, what is acceleration? Acceleration is d by dt of velocity or speed. So what is constant here? Velocity is constant, so it is d by dt of a constant, which is equal to 0. Therefore, the correct option is 0. But that's not what we want, right? We want to learn the concept behind this. So let us first try to understand the way to draw excuse me, way to draw the direction of tension. Okay, again, one common doubt which students often ask me: how to find the direction of tension. I'll explain you a couple of examples, then things will become absolutely clear to you. So say this is a fixed table. Okay, a body of mass m is kept here. Okay, there's a string here, sorry, a point of contact here, point of contact. It has been, two strings are being connected. Okay, and it is pulled by one force F1 on right side and another force F2 on the left side. Make use of a larger diagram. And suppose that you have a suppose that these are fingers wrapping this rope here. Okay, why fingers? Because we need point of contact. So what is the direction of tension? It's pretty straightforward. Direction of tension is always acting such that it is away from the point of contact. Acting away from the point of contact. Let us see. So this rope here, if it has tension T, okay, if it has tension T, it has 2 points of contact, one from the block and the other at the finger, right? So point away from the point of contact, acting away, my bad, acting away from the point of contact, say tension T1. Okay, let's do one more case. There are 2 points of contacts here. So where will tension act? Acting away from the point of contact, say T2. Again, we have point of contact here, acting away from the point of contact here, tension T2. Okay, simple example. Let's take one more example on a case like this. So a pulley is attached here. Pulley is attached. We have, wait. So say we have a string like this. We have a string like this. and at the end of the string there is a mass connected here, say of mass m. Another string like this, say mass m. Okay, now in this case let us try to draw the direction of tension. See, now this is only one string, right? There's only one string present here, so the overall direction would be t. So the overall magnitude would be t. Now the direction of this, see, let us first identify the point of contact. This is sorry. So say this point over here between the string and the block is one point of contact. There is one between the string pulley here, another between the pulley here, and the third one again with the pulley and the block, right? So how do you draw the direction? Away from the point of contact. How do we draw the direction of tension? Away from the point of contact. Tension T. Tension T. Point of contact away from it. Again, point of contact away from it. Tension T. Excuse me. So I would say this is the logic behind drawing the direction of tension. Okay. Having said this, let us move on to the question here. So I'll keep this as a reference, right? The direction of motion or direction of tension. And I'll draw the complete diagram. I'll enlarge this. I'll keep it as a reference. Okay. See, there's a minor correction here. Actually, this string is not present here. Yeah, something like this. Okay. Now let us draw the blocks individually. Yes, that is what I'm trying to cover here, is to make sure that you are able to solve any question using this concept. So the force acting here, right? And between m and 2m there is one connection. Now since there is only F acting here, there's only force here, but here there's a point of contact between string and the block, which means there would be tension acting downwards. That I'll write as T1. Okay. Now we have another block here, which is 2m. Now look at that. 2m has two strings connected, one towards m, the other towards 3m, right? So there would be point of contact here, string, point of contact here, string, and tension would be acting away from the point of contact. So we'll have here T1 and it is acting away from it. We'll mark it as T2. Okay. Now let us see with the case for the third block, which is the block with mass 3m. There is nothing acting downwards to it, but what is acting is force like this. There's a string, right? And tension would act along the string but away from the point of contact, and we have here T2 again, right? Same string. Now what we'll do is we'll try to club these diagrams together. Okay. So this is 1, this is 2, right? I hope you are able to decipher the concept here. And this is 3, right? So now that becomes the overall free body diagram. Okay. Now we'll also draw the free body diagram for the complete set, which means it goes like this. Add the overall masses. What are the overall masses? M, 2m, 3m, right? So I'll replace this complete this whole set of blocks with one big block, which measures, it's better to write down, I think, which measures m plus 2m plus 3m. What is acting on it? F is acting on it, which means the net direction is actually towards the positive direction upwards, positive J, positive Y axis. And it is given that the overall system is moving with constant velocity, right? See, from the figure, it can be very safely assumed that this complete set, if there is, excuse me, if there is a vector, force acting in the upward direction, it means that the blocks are moving upward like this, right? It's moving upward like this. It is not coming downwards. This was the original position. The block is moving upward like this. The block is moving upward like this. So it's here now. The block is not having any kind of horizontal movement. The block is not having any kind of horizontal movement. It is having only vertical movement. I repeat, the block is not having any kind of horizontal movement. It is having only vertical movement, right? So if you were to compare this diagram alone, the object is moving, sorry, the block when combined together, the block is having only vertical movement. It is not having any horizontal movement, which means if motion is along y axis alone, if motion is along y axis alone, it means that force along the x component is equal to 0, right? It means acceleration along the x component is equal to 0, because there is no force, there is no motion, there is no acceleration, there is no velocity, there is no acceleration, there is no force. Simple logic, okay? Which means the complete motion is now restricted to towards the y-axis. Now, the forces acting on this body would be Fy, right? And sum of all the Fy would actually give us the excuse me, would give us the F net, which would result in A net, right? So if you write the equation here, how do you write this? We can write that sigma Fy is equal to m into A net, right? Which is equal to m into ay. Why ay? Because ax equal to 0. Now, since the object is moving with constant velocity, acceleration along y direction would be equal to 0. So we have m into ay is equal to m into 0. Therefore, sigma Fy is equal to m into 0 is equal to 0. Okay, so sigma Fy is equal to 0 is what we derived. So what is the net force in the block of mass? 2m. So if we were to study only this block 2m, if we were to study only this block 2m, what we need to understand is we need to understand the free body diagram of 2m alone. So let us draw that one more time. So we have 2m here. Tension is acting away from the point of contact, which is T1. Tension is acting away from the point of contact, which is T2. So what is sigma Fy? Sigma Fy will be the difference here. The net direction of motion is acting upwards, so we'll take that force moving along this direction as positive and that moving opposing this direction as negative. So we have sigma Fy is equal to T1 minus T2, right? Now, this is sigma Fy is equal to T1 minus T2, and what would be the acceleration? This will be equal to mass into mass, which is 2m into all the bodies will have the same acceleration, right? So it will be 2m into A net. So we have T1 minus T2 is equal to 2m into what is A net? We derived it. A net is equal to 0. Therefore 2m into 0. Therefore in addition to this question, you can also maybe asked in a different way that T1 minus T2 is equal to 0, and therefore for this condition to exist, T1 should be equal to T2, and the sum of the forces acting on this is actually equal to 0. So I think sorry, I think this explains the overall application of direction of tension and how to resolve the forces along the x and y direction. If you want further explanation on tension, please post it after the class. Those students who are listening this online, you can post a comment. Okay, so yes, that's it. So maybe if you want, we can discuss multiple cases. One block on another block, maybe two or three blocks being connected by strings on a horizontal plane, on a vertical plane, on an inclined plane. All this we can resolve tension as we did in the second question for mg. Like mg cos theta, mg sin theta. We can have t sin theta, t cos theta. Those kind of questions. If they are in the previous questions, I'm pretty sure they would be. We'll have a detailed discussion. If not, if you want any question in specific, please, I request you to write, post it. You can write it directly to me, or you can post it in the comment box. We'll get back to you. Okay. Uh, yeah. So that being said, let's move on to the next question. Question number 4. A balloon with mass m is descending down with an acceleration where a is less than g. How much mass should it be removed from it so that it starts moving up with an acceleration a? So we will discuss this question in two different parts. Okay, so let's discuss the first part. So what is the first case? It is given that the mass of the balloon is m, right? Mass of the balloon is m. Mass of the balloon is m, and it is descending down, right? So the net direction of motion is acting downwards. Okay. How much mass should be removed? Okay. So let us discuss only the first part now. So assuming this to be the balloon with mass m, what are the various forces acting on it? See, the first force acting on it would definitely be the weight, which is mass into acceleration to gravity, right? Now we need to understand that since it is a balloon, it will definitely experience the force of buoyancy, right? So there are two forces acting on this: force of buoyancy and the weight. Now, what is the net direction? See, the object is descending downwards, right? It is descending downwards with acceleration a. Okay. So all those forces, my bad, all those forces which are along the direction of motion, irrespective of the number, they should be taken as positive. So what I'll do, I'll consider this as positive mg. All those forces which are against the direction of net motion will be taken as negative. So I'll take it as negative fp. Okay. Now, see, as we did in the previous problem, right? This question, so if you have to understand this, okay, let me explain that part also. So see, this is the balloon here, right? And this balloon has movement only towards, okay, so it was here. It has movement only in the y direction. Either it is descending downwards or it is descending upwards. Either it is descending downwards or it is ascending upwards. So the movement is either top or bottom. It is neither moving to the left nor to the right. So there is no movement along the positive x or the positive negative x. There is movement along either positive y or negative y. So what is the key point? No movement along the positive x nor the negative x, right? Okay. So we can say that since there is no motion, Along which direction? Since there is no motion along the x direction. So if there is no motion, it simply means that velocity along x direction is equal to 0. See, if velocity along x direction is equal to 0, what is acceleration along x direction? That is also equal to 0. If velocity along x direction is equal to 0, if acceleration along x direction is equal to 0, what is mass into acceleration on x direction? That would also be equal to 0. Therefore, what is ma? Ma is fx, right? Ma is f, and therefore max is fx, and therefore fx is also equal to 0, right? Now, what do we have to find out? Is Fy. So, what is the equation for Fy? Fy would be m into Ay, right? M into Ay. Now, since there is no Fx here, since there is no Ax here, since Ax is also equal to 0, I'll take Ay as A, so get it as m into A. Okay? Now, what is Fy? Fy denotes the sum of forces, what? Sum of forces acting along the which direction? Acting along the y direction. Acting along the y direction, right? Now, how many forces are there acting along the y direction? We have one force Fb and the other force mg. And how will you write the sum here? You will write this as positive mg, right? Positive mg over here minus the FB, right? Minus FB. And what would this be equal to? This would be equal to M into A, right? So this is one part of the story. What is the second part? Mass is removed and it starts moving upward with an acceleration. So let us discuss that part. So now what we have is, there was a balloon with mass m, okay? Let's assume that some amount of mass is removed from it. So say it's like this now, okay? And the removed part weighs m dash. So there was m. What has been removed? M dash has been removed. In which case, what is the mass of the leftover block? It would be m minus m dash. Okay. Now, if this is the case, what are the forces acting on it? See, we know that the very first force acting on this body would be definitely the weight, and the weight being m minus m dash into g, right? And what is the buoyancy force acting here? It would be FB. But this time you need to understand that the moving up with it's moving up with an acceleration, right? So the net direction of motion is acting upwards. And when net direction of motion is acting upwards, what do? You mark all those forces along that direction, in which in this case is upwards, as positive. So all those forces which are along the up direction will be considered as positive. So we'll mark this as positive. And simultaneously, when all those forces along the direction of motion are considered as positive, all those forces which are against the direction of motion here would be considered to be considered to be negative. So we'll put a negative sign here. Okay. Now again, there is no direction, there is no motion along the x direction. So we have ax is equal to, okay, therefore vx is equal to 0, and therefore ax is equal to 0, and therefore we have m into ax is equal to 0, and therefore fx is equal to 0. So the only set of forces here acting here would be along the y direction, and therefore we need to find out Fy, and we have the formula sigma Fy is equal to m into Ay. Now instead of m here, we actually have m minus m dash, which is m minus m dash into Ay. And since there is only one component of Ay, there's only one component of acceleration along the y, and since Ax is equal to 0, I can write this as m minus m dash into A. Okay. Now, if you were to ask me how does that come, so it's very simple. What is A is equal to? A is equal to root of ax square plus ay square. Ax square is 0, so this is equal to root of ay square is equal to ay. Therefore, I can write that a is equal to ay. That's the logic. Okay. Uh, right. So we have sigma fy is equal to m minus m dash into a. Yes, that's there. So what is sigma fy now? Okay. So we have one force fb along the positive direction, right? So we can write that as positive fb, and then we have minus this force over here minus m dash into g is equal to m minus m dash into a. Okay. So if you write this further, what we get is fb minus mg minus into minus plus m dash g is equal to ma minus m dash a. Okay. Now let us bring these two equations together. Which ones? This one. This is the first equation. Let us bring this one also. This is the second equation. Let me erase out the things that are not required. Okay. Now what we'll do is we will, as in the case of every problem here, what we'll do is we'll add these two equations. So what do we get? What we get is fb minus mg plus m dash g plus mg minus fb is equal to ma minus m dash a plus ma, right? Now see, which all terms will cancel off? fb minus fb is 0, right? Minus mg plus mg is 0. And ma plus ma is equal to ma plus ma is 2ma minus m dash a, right? And if we bring this ma dash to the LHS, what we get is m dash g plus m dash a is equal to 2ma, right? And therefore, if you take m dash common from here, what you get is g plus a is equal to 2ma, and therefore m dash is equal to 2ma the whole upon g plus a, which gives us the correct option as option A. Okay, so I'll just summarize the entire solution one more time. So where did we start? We took the first case, right? What was the balloon doing? The balloon was descending downwards. So net direction is towards negative y. It is acting downwards. So all those forces acting along negative will be acting downwards would be taken as positive. Weight is acting downwards, therefore it is positive. Buoyancy is acting upwards, therefore it is negative. Now the other case, mass m dash is removed, remaining mass is m minus m dash. Net direction is acting upwards. All forces acting upwards should be considered as positive. Therefore, buoyancy is considered to be positive. All those forces acting against this is mg. It is considered as negative. Free body diagram, one equation, second equation, and two equations. What you get is m dash is equal to 2ma by g plus a. Okay. So, well, I think this was question. Okay, it's here, right? CBSE AIPMT 2014. So there was a switchover between NEET and AIPMT back again. So that was the only year, I would say, after 2013 that the exam was conducted as AIPMT. Later on, it was merged with AIMS and with NEET. So I would say a really good question, for definitely above the standard of a typical state level entrance exam, and definitely not as high as AIMS. When I say this, I'm referring to the year of 2014. After that, there was after 2017 there were dramatical changes in the pattern, but I would say this was a really good question. So yes, that's what I have to say about the question here. Let's move on to the next question. M is indicated by the force time graph shown below. The change in momentum of the particle over the time interval from 0 to 8 seconds. 0 to 8 seconds is okay. So this, I think, is a very a direct application of the formula and area under the graph of FT graph, right? So What is the formula? The formula says that delta P is equal to F into delta T, right? Which means if delta P is plotted, sorry, if delta P, if F is plotted along y-axis and delta T is plotted along x-axis, then area of the area under the curve is what we get as y into x. So if you compare y as F, so if you have a graph where the y-axis represents force and x-axis represents time, and if there is a graph here which represents the ft curve, then the area under this graph, right, this shaded region here, what would this shaded region be equal to? This shaded region will be equal to the area which is here delta p, right? So we have the graph here. Let us now find out the area. So for those students who are at least here for the first time, right, I don't want to skip any steps here. I want to make sure that you get the conceptual clarity clear. That's why I'm going in this depth. So to make it even more clear, what I'll do is I'll label these points as O, A, B, C, D, E, F, G, and H. Okay, so what is the area of OAB? Let us first find out. So maybe what we can do is we can use different colors to highlight this area. So this is one color, another one. So we've got three area under the curves here, right? So let us first find out area 1. Let us first find out area 1. So what is area 1? Draw it if you have a confusion, right? Practice it a couple of times and then you may not need to draw it, but in the initial stages, please do draw it. So we have 0, A and B, right? And this distance is given to us as 2, and AB from the figure is 0 to 6. This is 6, okay? So what is the area? Area is area of triangle OAB, which is equal to half into 2 into 6, which is 6. Now coming to area 2. Area number 2, which is, okay, I'm going to skip area number 2 for a second. I'll come back to it. Let us discuss area number 3. Area number 3. Okay. So area number 3 goes like this: y-axis, x-axis. It is 3 here. It starts from E, F, G, H. Isn't it? E, F, G, H. So, which is actually area of rectangle EF, GH, which would be equal to length into breadth. Say EH into GH. What is EH? Measured as 4 to 8. So this much is 4, right? And GH here would be 0 to 3. This is 3. So we have got 4 into 3 is equal to 12. Now let us specifically discuss about area 2. So area 2, the curve is B, right? C, D, and E. So what is the area? Area is actually area of rectangle BCDE, which is length into breadth. So let us say BC into CD. I'll write this separately here. BC into CD, which is equal to, what's the measure of BC? See, BC here is 0 to 3 is 3, right? It's 3 into CD is this much, 2 to 4 is 2. But this is where most of the students make a mistake, because if you observe the y-axis here, it is negative y. So BC corresponds to negative y. So it is 0 to minus 3. And therefore what you see, BC here is minus 3. So what you get the second area is minus 6. In which case, if you add these three areas, what do you get? 6 plus minus 6 plus 12, which is equal to 12. Okay. Now look at the way how tricky the options are. If you would have skipped this minus, I repeat, if you would have skipped this minus, then what would the answer look like? It would look like 6 plus 12, which is equal to 12 plus 12, which is 24, which is option A. Yeah, so that remains the case with almost every possible tricky MCQ question. To it will make you deceive the correct option to be the first option, if not the one, then if not the second or the third one. So yeah, that happens. But I was just trying to make you feel cautious the next time you see questions over graph. Okay. All right. Students, let us now move on to the next question, the fifth question from the series. A system consists of three masses m1, m2 and m3 connected by a string passing over a pulley P. And the mass m1 hangs freely, and m2 and m3 are on a rough horizontal table with the coefficient of friction being mu. The pulley is frictionless, and of negligible mass, The downward acceleration of the mass m1 is okay. So, to understand the concept of this, or to understand how to solve these kind of questions, we'll for the initial set of problems, what we'll do is we'll try to solve every question in the detailed way, and then as we slowly pick up pace, we'll start to do use formulas directly. Okay, so I'm not going to use any formula directly here. Instead, we'll see how to solve each and every subpart of the question very correctly. Okay. So first thing is to identify the direction of motion. So the direction of motion here is downwards, right? The downward acceleration is being said. Downward acceleration. Okay. So direction of motion is downwards. So what will be the way to choose? What will be the way to choose the sign convention? Along the direction we'll choose it as, along the direction of motion we'll choose it as positive, and against the direction of motion we'll choose that as negative. Okay. So this is applicable for the first mass m1, right? This is applicable only for the first mass, not for the second mass and third mass, because they are moving in a different direction, right? So this is negative. So we're talking about only about the first mass. So now what I'll do is I'll draw the first mass separately. Okay, so let's do that. So this is the first mass, right? This is the first mass, which is m1. Now let us first draw the diagram. Draw the free body diagram and represent the various forces acting on it. See, it is the first force would be m1 into g acting downwards, and the upward force. How do we mark that? See, this is the point of contact, and tension in the string will be always acting away in the direction that is away from the point of contact, right? Away from the point of contact. So if we have to draw the free body diagram, we have to look like this. We have tension acting opposite direction, right? And then we have m1g acting in the downward direction. And what is the net direction of motion? The net direction of motion is acting downwards. So what do we do? Direction of motion. Along the direction of motion, we'll take things to be positive, and against the direction of motion we'll take it to be negative. As we did in the previous questions, we need to understand whether the motion isn't taking place in the x direction or in the y direction. So let us see. Now, wait. So if we closely try to understand the motion of this object, this mass m1 here, see, this mass m1 is moving in. It was, say for example, this m1 was hanging here, right? So this m1 is acting, it is moving downwards, right? The downward acceleration is being asked. So the mass is moving only downwards. It is neither moving upwards nor is it moving in the sidewise direction. So the pulley was connected to the mass like this, right? And then the mass was moving only downwards, and it has neither neither a movement towards left nor movement towards the right. So it is acting, it is moving only in the downward direction. Okay, so that's which means considering this body, there could be fx and fy. See, if there has to be fx and fy, then we can write that f is equal to root of fx square plus fy square. Now, what is fx? Fx is equal to, right? Fx is actually equal to m into ax. And what is fy? Fy is equal to m into ay. Now, is there any motion in the x direction? No. If there is no motion in the x direction, it implies that velocity along the x direction is 0, which otherwise implies there is no velocity, there has to be no acceleration, right? So we can write that fx is equal to m into ax, which is equal to 0, and therefore fx is equal to 0. Okay. Now what is fy? See, fy is equal to, so the net force we have to take into account here. So what did we say the net force? How many forces are there? There are two forces. And how do we write that? We write the positive forces first. So let me write down positive positive m1g first. So we have positive m1g. What is the next force? The next force is minus tension is equal to, what is the mass? Mass is m1 is equal to m1 into ay. Now since there is only ay component, I can replace it with y, with replace ay with a. Okay, so the equation we get is mg minus t is equal to m1a. So let me highlight this equation. Over here. Now we'll use the same concept to solve the free body diagram for the next for the rest of the two blocks as well. Okay, so for that let me take a different space. Yeah. Now let us discuss about the second body here, which is m2. Okay, m2. So for m2, we know that there's a surface here, right? And a pulley is attached to the surface, and a string is passing through the pulley, which is connected to the mass, m2, which also is connected to a third mass m3, which is not something we will discuss here. So let us try to label the forces here, but before that, first let us identify where is the net direction of motion happening in. See, if m1 is going downwards, I repeat, if m1 is going downwards, it simply means that m1 is pulling m2 and m3 along m1, right? So m2 and m3 will be pulled along with m1. Now m2 can't drop down. Why? Because there's a surface here. m3 can't drop down. Why? Because there's a surface here. So the only possible direction of motion for m2 will be to follow the table like this, along the pulley, right? So follow the table like this, which means m2 and m3 will follow the table like this. It will move towards the left. Okay. So the net direction of motion is towards the left. Let us now draw the various forces. So we know that there is a string attached here as well. So tension will be originating from the point of contact, but away from the point of contact. Tension will be originating from the point of contact, but away from the body, right? Away from the body. So this will be the tension acting on it. Now we're not done here. Why? Because it is given that it is on a rough horizontal table. So it's on a rough horizontal table, which means what is acting here? friction is also acting. So we know that if the direction of motion is towards the left, then friction will be acting towards the right, because friction is an opposing force. So if the direction of motion is towards the left, then we have friction which is acting towards the right. So friction would come into picture here, and frictional force would be acting. Let me write it as Fr. Okay. What else do we have? We also have the normal reaction acting here, and weight of the body acting downwards. Weight of the body acting downwards, M2G. Okay. Now let us find out Fx and Fy. See, is there any motion in the vertical plane? For this mass M2, motion is taking place only along the x direction, right? Motion is along the x direction only. So if the motion is along the x direction only, what does it imply? It implies that Vx is equal to 0. I'm sorry, not Vx. Vy is equal to 0. And if Vy is equal to 0, it means that Ay is equal to 0. And if Ay is equal to 0, it further implies that M into Ay is equal to 0. What is Ma? Ma is F, so May is Fy, therefore Fy is equal to 0, right? And if Fy is equal to 0, this gives an indication that N minus M2G is equal to 0, right? Or otherwise, well, to be more precise, we can write that if Fy is equal to 0, we can write that N is equal to M2 into G. Okay, so this is the condition with Fy. Now let us discuss what happens with Fx. So when we consider forces along the x direction, let us draw the free body diagram. So we have an mass here. My bad. So there is tension here T. Okay. Wait, should we write T1? Maybe that would help us, right? So let us write it here, T1 here, in which case we'll have to replace the entire terms here also. So this is also T1, this is also T1. Okay, right, now it makes sense. Okay, so we written a T1, right? T1. And we'll write this tension as T2. So T2 is acting towards the left. So T2 is acting towards the left. And what else is acting? We also have friction force Fr, which is acting towards the right. Now, what is the net direction of motion? The net direction of motion is towards the left. The net direction of motion is towards the left. Therefore, this much direction of motion. So all the forces acting along the direction of motion. All the forces acting along the direction of motion, which means there's only one force here, which is T1. So T1 is acting along the direction of motion. Therefore, T1 should be taken as what? T1 should be taken as positive. Now, T1 should be taken as positive. Fr would be taken as negative, right? Fr would be taken as negative, and T2 would also be taken as negative. So if we write the equation here, how do we write this? We write that sigma Fy is equal to M into Ay. So what is sigma Fy? The sum of all the forces. So if we take the sum, we have plus T1. So we have plus T1 minus T2, then minus Fr is equal to M into Ay, right? Okay, so what we need to understand here is what is, okay, let me rewrite this equation one more time. So we have T1, right? T1 minus T2 minus, now what is Fr? See, we know from the equation of friction that Fr is equal to mu into, right? Mu into N. And what is N here? N is M2 into G, right? So Fr is basically equal to mu into M2 into G. So if I write it over here, Fr is equal to mu into M2 into G, which is further equal to M into Ay. So instead of Ay, I can replace it as A, right? Because all the systems have common acceleration, A. Okay. Now, okay, so that's it with the second mass. Let us now discuss about the third mass. So this is about M2. Now so the table. So let us first draw the table. What is attached to it? A pulley is attached to it, right? Mass as M2 is connected, which we don't need to consider here. So we need to consider only the mass M3. The only mass connected here is M3. And since there is a point of contact here, tension will be acting along this direction, right? Sorry, tension will be acting against the direction, against the point of contact, away from the point of contact. So let me mark this as T2, right? This would be T2. Did we take T2 there? Yeah, T2. Okay. So it's T2. What's the net direction of motion? Net direction of motion is towards the left. And what else will be acting here? Since both of them are on the same table, frictional force Fr would be acting, right? The vertical forces here would be normal reaction N and weight acting downwards, which is M3 into G. Now let us try to write down. Okay, let us not skip steps, right? Let us write things in detail. We'll write down both the Fx and the Fy values here. So the direction of motion here, direction of motion is only direction of motion, or say direction of motion is restricted towards the x-axis, which means there is no motion along the y-axis. Now, if there is no motion along the y-axis, what does it further implies? It implies that Vx is equal to, it implies that Vy is equal to 0. And if Vy is equal to 0, Ay is equal to 0. And therefore, if Ay is equal to 0, M into Ay is equal to 0. And therefore, if M into Ay is equal to 0, what is F? F is equal to Ma. So what is M into Ay? It is Fy. So Fy is equal to 0. And therefore, we can say that normal reaction is actually equal to M3 into G, right? So this is the case with x direction. Sorry, y direction. Now let us resolve the forces along the x direction. So again, what do we have? Along the x direction, we have velocity in the x direction, we have acceleration in the x direction, and therefore we have mass into acceleration around the x direction as well. So we can write that Fx is equal to m into ax. Now let us draw the free body diagram here. So if we draw this mass m3 here, what are the various forces acting along the x direction alone? So we have one force acting along is Fr, right? And the other one acting along the direction of motion is T2. So the net direction of motion is towards the left. And we'll mark that force as positive. And the one which is acting towards the right, we'll take it as negative. So sigma Fx, so when we take actually sigma Fx is equal to max, what do we write here? We can write that plus T2, right? So we can write that plus T2 minus Fr is equal to m into, instead of ax, we can write a here, right? Okay, so my bad. This should here be not ay, right? It should be ax. My bad. Oh, I wrote here sigma fy as well. Okay. Oh, right. I'm sorry. I'm so sorry for that. So it will be mx is equal to ax. Yeah. Okay, that's correct now. Okay. Okay. So it's T2 minus Fr is equal to. Now, what is m here? M is m3, right? M is m3. So we have m3 into a. Now, what is Fr? We know that Fr is actually equal to mu into n, right? So Fr is equal to mu into in. What is n? N is m3 into g. So we have m3 into g here. So this becomes mu r Fr is equal to mu into m3 into g is equal to M3A, right? So let me highlight this equation as well. Now let us bring all three equations together. Which all are we talking about? So we have this equation number 1, okay, and from the second case we have, so equation number 1, equation number 2, and we have equation number 3. Equation number 3. Okay. Now we'll try to solve these equations simultaneously. How will we do that? Simple. We'll just add these three equations together. We'll add the LHS and RHS together. So I'll write the tension portion separately. So we have T2 plus T1 minus T2 minus T1, right? Minus mu into M3G minus mu into M2G plus M1G is equal to M3A plus M2A plus, oh wait, did I write M here? Sorry, it's M2. M2A plus M1A, right? Now let's see what all things will cancel off here. T2 minus T2 0, T1 minus T1 is 0. Then what we have here is, if we take minus mu common here, take minus mu common here, so we take minus mu g as common. What do we have in the bracket? We have M3 plus M2 plus M1 into G is equal to, A is common, A into M1 plus M2 plus M3, right? Now, we need to go back to the question because we are missing on some point, which, oh, it is given in the question that M1 is equal to M2 is equal to M3 is equal to M. Okay, right. Now let us come back. So in this case, if M1 is equal to M2 is equal to M3 is equal to M, then this overall equation will modify to minus mu g into, right, M plus M plus M into G is equal to A into M plus M plus M, right? And what will this give us further? 2M into mu G plus mg is equal to 3m into A, or 3m, okay? In which case, what else is common here? If we take mu into G common, okay, let's cancel out m first. So this becomes a minus 2 mu G plus G is equal to 3A, right? And what is that we need to find out? We need to find out the value of acceleration. So A will be equal to, take G common, minus 2 mu plus 1 the whole upon 3, or A is equal to G into 1 minus 2 mu upon 3, which gives us the final answer as G into 1 minus, this is option 1 minus 2 by 3, option C. Okay. So we'll go through the problem once again. So pulley, M1 is acting hanging freely. M1 weight, tension is acting away, no horizontal motion, no horizontal motion, only vertical motion, forces balance. Equation number 1. Second case, M2 is sliding towards the left, no motion along the y direction, motion is only along the x direction. T1, T2, two tension acting, friction is acting because the table is given to be rough. Fr is equal to mu into n, Fx equal to max, against the motion negative, Fr is against the motion negative, T2 is against the motion negative, towards the motion T1 positive, towards the motion T1 positive, T1 positive, negative negative. Equation number 2. Now for the third block, no tension here, only friction acting here. T2, Fy is 0, sigma Fy is 0, and n is equal to m2g, right? So we'll actually have to mention the sigma Fy here, right? That would be more correct. Sigma Fy equal to 0, and n2 is n is equal to m2g, Fy is equal to mu n, Fy is equal to mu n is m2 m3g, so it is m3 into g. Fx, two forces acting along the direction of motion is T2, acting against the direction of motion is Fr, so plus minus, third equation. And then what do? We bring all these three equations together. We add them, then we invoke m1 is equal to m2 is equal to m3, m, then we just find out the answer. Okay. So that's how we approach any question based on block, tension, block, and pulley, all kinds of these questions. Okay. So you separate these, treat these values separately, right? You treat these cases separately, and then solve the individual free body diagrams. And then what we do is we try to come up with the necessary equations and solve all of them together. Okay, right. Having said that, let's move on to the next question. Force F is equal to alpha I plus 3j plus 6k is acting at a point R is equal to 2i minus 6j minus 12k. The value of f, which the value of f for which the or at which angular momentum about origin is conserved is. Okay, so see, before we go much into the solution, well, see, if you were to ask for the simple solution, it will go like this. What is torque is equal to? So we have 2 is equal to vector r cross f, and this is equal to 0. So all what you need to do here is find out this determinant ijk. What is r? R is 2 minus 6 minus 12, and what is f? F is alpha 3 6. Equate this to 0 and you will get the value as alpha. Simple. But that's not the point here. Since we are trying to understand the concept behind every question, what we should do in detail is to understand the logic behind every term which is given to us here. So we'll start with at a point. Okay. Force is acting at a point, so there's not much detail given at a point. The value of F as angular momentum is about origin. Okay. So what I would like to do is I would like you to understand the basics of momentum here. Okay. So let's first write it down. So when we say the term momentum, we should be more specific about what kind of momentum are we mentioning about. So momentum, it can either mean linear momentum or it can mean angular momentum, depending upon the context. Now, when it comes to angular momentum, we again have two types. Let's say two, not two types, would be two scenarios where an angular momentum could be defined. One in which the object considered as a point object. Okay, is a point object or regular figure to be more precise, and the other one, angular momentum of a rigid body, or maybe an irregular body, or or let us use a what other word would be irregular, or maybe an extended object. That would be more correct. Okay, of an extended object. So point object or a regular object. A regular wouldn't be a more precise here. Point object or a rigid body or an extended object. Okay. Now let us see the difference between angular momentum here. So when we say linear momentum, okay, let us first understand the different cases properly, then we'll be able to figure out well. So if we were to discuss about linear momentum, what is this? What is the picture that would come to our mind? See, there's an object of mass m. Okay, it is moving with velocity v, and in this case, the linear momentum is nothing but the product of mass into velocity, which is mv. Okay. Now let us see the case of angular momentum. Angular momentum. Angular momentum. So the scenario here is there is a ball of mass m, right? There is a ball of mass m. Okay, there is a ball of mass m, and what's happening to this ball? This ball is executing. It is executing a rotational motion. It is executing a rotational motion. Okay, passing through an axis, at a distance r, passing through an axis at a distance r. So let us try to visualize that. And how would we do that? Say, so there's a ball here. This is mass m, okay, and this is the axis, okay. Say, okay, let's a ball of mass. Let us say it is tied to a string. Tied to a string. Yeah, now it will make more clarity here. So this is the string here, right? And this is the mass. This is the ball of mass m, okay. And what's happening to this? It is again moving with the. It is given a velocity like this, right? And what will it do? It will execute a. It will execute a circular motion. It will execute a circular path like this. It will execute a circular path like this, right? So this is execute a circular path like this. In this case, what is angular momentum? In this case, angular momentum is defined as L. Angular momentum is defined as L, which is equal to linear momentum P into the distance, into this distance, which we'll write it as R. Okay, so we have linear momentum into R, and therefore L is equal to mv into R, right? So this is linear momentum. Also, this is angular momentum for a point object. Now what we need to understand further is angular momentum of an irregular object, something really important. So let's try to understand the derivation of this. So we have angular momentum of an extended object. Of an extended object. So let's try to understand the concept behind this. So here what I'll do is, we have a reference axis here, right? And earlier we had a string which was attached to a ball. Instead of that string and the ball here, what we have is a rod. A complete rod is kept here. So we have a complete rod of mass m, of course of length r, and the same parameters apply here. This entire rod is moving with velocity v. Okay, so we're not going to discuss this part now. We just have the comparison here. So how will we understand the angular momentum here? Let's see the concept here. So understand the angular momentum, what we are going to do is we're going to split this mass or a rod of mass m into different smaller masses. So say I divide this into m1, m2, m3, m4, and etc. up to mn. Okay, and then I'll consider individual masses and try to find out the angular momentum and then add it up. Okay, so why am I doing this? What I'm trying to do here is I'm trying to find the angular momentum of the rod, which I'll find it as angular momentum of mass m1 plus angular momentum of mass l2 plus angular momentum of mass m3, etc. up to angular momentum of mass n. This is what I'm trying to do. Okay, so instead of finding the angular momentum of the complete rod, what I'm going to do is I'm going to compare. So I'm going to find out the individual angular momentum of these blocks and then add, so that this gives the complete rod. Okay, so that's logic behind this. Now, how do we find the angular momentum of this mass m1? This mass m1. Let's see. See this v, when we say that the rod is given linear velocity v here, it doesn't mean that this m1 will also receive v. Why? Because m1 is not at r. m1 is actually at a distance r1, which means there would definitely be a change in velocity, right? And here the angular velocity experience would be different. Okay, the angular velocity experience would be different. I'm sorry, the linear velocity experience would be different, whereas the angular velocity would remain the same. Now, what would be the linear velocity experienced here? See, that would be equal to v1, which by the formula we know that what is v is equal to r omega. So here v1 would be equal to r1 into omega, right? So we have v1 is equal to r1 into omega. Now let us write down here. So what is L1 or moment of inertia? Sorry, not moment of inertia. What is angular momentum of m1? That will be equal to p into, right? That will be equal to p into r1, right? So what is p? P is m into v1 into r1, right? So we have m into v1 into r1. Now let us understand the next mass, which is m2 here. Now m2 is at a distance of r2. Okay, understood. M2 is at a distance of r2. Now this again will be experiencing an angular velocity omega. Now v2 here would be equal to r2 into omega, right? Because it's a different mass and it's a different velocity being seen here. So if we have to write the angular momentum of m2, that will be equal to Lm2 is equal to, okay, now we should write p1 into r1. So we have p2 into r2. What is p2? p2 is m1. So p2 is m2 into v2, m2 into v2 into r2, right? Okay. Similarly, okay, let me draw one more diagram for the clarity. So say this is the third mass here, right? Third mass, m3. Now where is m3 located at? m3 is at a distance. m3 is at a distance of r3, right? m3 is a distance r3. And what is the velocity it is experiencing? This will experience a velocity v3, which would be r3 into omega towards that direction, right? So we have to write the mathematical form. So we angular momentum of m3 is equal to linear momentum of p3 into distance r3, which is equal to m3 v3 into r3. See, one thing that I can assure you is this question shouldn't be asked from a chapter, the laws of motion, because it's purely a concept related to circular motion. But the reason why I'm detailing here it maybe you'll understand better when we come to the discussion of rotation motion if we have a preliminary understanding about the topic. Okay, so now let us add these equations. So let me write Lmn is equal. What will be Lmn? Lmn will be equal to Pn into Rn, which is equal to Mn Vn into Rn. Okay. Now we'll add all these equations. What do you get? So when we add this equation, we'll add the LHS separately, which is L of m1 plus L of m2 plus L of m3 plus etc. up to L of mn is equal to m1 v1 r1 plus m2 v2 r2 plus m3 v3 r3 plus etc. up to mn vn rn. Now, what is lm1 plus lm2 plus lm3? We have it here. So lm1 plus lm2 plus lm3 etc. up to n terms is actually lnet, which is the total angular momentum. So we have this is total angular momentum. Lnet is equal to m1 v1 r1 plus m2 v2 r2 up to n terms, right? Okay. Now, I'm going to make a small rearrangement here. And how will I do that? I'll write like this. m1 r1 v1 plus m2 r2 v2 plus m3 r3 v3 plus etc. up to mn rn and then vn. Okay. And why are we doing this? We'll come to it. Now let us try to. Some of you might be wondering why did I write r omega and why did I not use it so far? Let's bring that concept now. So what is v1 is equal to r omega? What is v2 is equal to r2 omega? What is v3 is equal to r3 omega? Now we'll write those values here. So this will be equal to m1 into r1 into what is v1? v1 is r1 into omega plus m2 into r2 into what is v2? From here v2 is r2 into omega plus m3 into r3 into what is v3? v3 is r3 into omega plus etc. up to mn rn. What will be vn? vn would be rn into omega. Okay. Now look at the beauty of adding these equations. So what we get is m1 into r1 would be now be r1 square would be r1 square into omega, right? Plus m2 into r2 would be r2 square into omega plus m3 into right r3 square into omega plus up to n terms we have mn into rn square into omega, right? Now what is common in all these terms? What is common in all these terms? Right, we have omega, which is common in all these terms. So let me highlight that part also. So omega here, omega is common to all terms, which means we can pull out omega out of these terms, right? So if I pull out omega out of these terms, what do we have in the rest terms? What we have is m1 r1 square plus m2 r2 square plus m3 r3 square etc. up to mn rn square. Now this would further be equal to well, let's write lnet LHS is equal to RHS, which is sigma of m into r square times omega, right? Why? Because m1 r1 plus m2 r2 plus m3 r3. Okay, let me write down that also. So say we have m1 r1 plus m2 r2 is equal to sigma mr, right? So m1 r1 square plus m2 r2 square would be equal to sigma mr square. Simple logic. Okay, so that's how we get it. So that's how we get sigma mr square. Now what is Lnet? I abbreviate that as L is equal to what is sigma mr square? See, this is where I say this question is not asked from laws of motion. This is purely based on the angular, circular motion. Now what is sigma mr square? We know that is moment of inertia I. So we have L is equal to I omega, right? So L is equal to I omega. So we have three formulas for angular linear momentum. One is linear momentum, which is m into e. Other is L is equal to m into v into r, second one, and the third is L is equal to I omega. Okay, so these are three different formulas related to momentum. Okay, now let us come back to the question here. So what did we say in the discussion so far? We said that linear momentum P is equal to mv, and then we said that angular momentum about a point object, right? Angular momentum about a point object is L is equal to mv into r, and then we said for a rigid body, angular momentum L is equal to I into omega, and we will make use of the formula. P is equal to me. Sorry, L is equal to me into r. Now let us go to the question here. The angular momentum about the origin is conserved. So let us write like this: angular momentum is conserved, right? Angular momentum is conserved. Now see, when we say angular momentum is conserved, this actually means that the net external force, the net external torque acting on the body is equal to 0. This is what this means. Okay, net external torque acting on the body is 0. I'm not going to take you to the concept there. Let us first understand the mathematical part of this. So the angular momentum is conserved, right? So when we say angular momentum is conserved, this otherwise means that angular momentum initial should be equal to angular momentum final. Right, angular momentum initial should be equal to angular momentum final, or otherwise this can be said that angular momentum initial minus angular momentum final is equal to 0, right? Or we can say that change in angular momentum, which is initial minus final, is equal to 0. So we can say that delta L is equal to 0. Now what does delta L is equal to 0 implies? This implies that angular momentum L is actually a constant, right? Okay, now coming to the vector notation. This is where most people make a mistake, and we'll discuss more on this when we come to rotational motion. How did the cross product come into picture? Not now. Now what is vector L? Vector L is r cross linear momentum, which is P. Okay, so I can write this as r cross, what is P? P is mass into velocity vector v. Okay, so if I write this further, I can write vector L is equal to r cross m cross v. Now I'll write down this equation one more time, and then this time what I'll do is I'll differentiate both the equations with respect to time. Okay, I'll differentiate this equation with respect to time. In this case, what do we get? We get dl by dt is equal to vector r cross, vector r cross m into dv by dt, right? This further gives us that d by dt of L is equal to r cross m into what is dv by dt? It is the acceleration vector a, right? So we have dl by dt is equal to r cross, what is ma? Ma is nothing but the vector force F, right? So we have dl by dt is equal to r cross F. This is the formula what we'll use here. Now, since angular momentum is constant here, what is dl by dt? See, d by dt of a constant is actually equal to 0, right? So, okay, let me explain that since beginning. So d by dt of x square, d by dx of x square is 2x, but what is d by dx of 3? It is equal to 0. So the derivative of a constant is 0. Similarly, d by dt of k is equal to 0. Similarly, d by dt of L is also equal to 0. So we have r cross F is equal to, right? R cross F is equal to 0. Okay. So if we were to write this in a much correct way, so this derivative of the vector is equal to 0, right? So what we get is actually, what we get here is actually a 0 vector. To be more precise, 0 vector. Now let us bring in the values here. Given in the question, what is given? We given that what is vector r? The vector r is given to us as 2I cap minus 6j cap minus 12k cap. What is vector f given to us? Vector f is given to us as f is given to us as alpha I cap plus 3j cap plus 6k cap. Okay. Now, so r cross f is equal to 0 is what we get, right? So we have vector r cross vector f is equal to 0 vector, which is equal to 0 I cap plus 0 j cap plus 0 k cap, right? So if you take magnitude on both sides, if you take, okay, let us first do it the other way around and then I'll explain you the mathematical form as well. Now what is vector r cross f? That we know it is equal to determinant ijk, right? Determinant ijk 0I plus 0j plus 0k. R cross f means we'll first write the values of r here. 2 minus 6 minus 12, and f is alpha 3 and 6. Okay, right. So from here we can expand the determinant. So write this as I. Okay, let us expand this directly. So I into determinant of minus 6 minus 12 3 6 minus j into, right? So we have j is equal to 12 alpha 6 2 12 alpha 6 plus k into, what do we have here? 2 6 alpha 3 2 minus 6 alpha 3, sorry, I cap j cap k cap is equal to 0 I cap plus 0 j cap plus 0 k cap, right? So this would be I cap into 0 minus j cap into 6 and 2 is 12. So what we get is 12 minus 12 alpha plus k cap into, what we have here is 6 plus 6 alpha, right, is equal to 0 I cap plus 0 j cap plus 0 k cap. So if you write down the simplified form of vector, what we get is 0 I cap minus, wait, are we missing anything here? 12 minus, wait, I did a mistake. See, it's 6 into 2 is 12, minus into minus become plus, right? Plus 12 alpha. My bad. It's minus 12 here. Okay. So minus j into, we have as 12 plus 12 alpha into j cap plus, what we have is 6 plus 6 alpha into k cap is equal to 0 I cap plus 0 j cap plus 0 k cap, right? Okay, now let us compare these two terms here. If we compare the j component alone, what do we get? What we get is minus of 12 plus 12 alpha is equal to 0, right? Okay, minus of 12 plus 12 alpha is equal to 0, which means 12 plus 12 alpha is equal to 0, which means 12 is equal to minus 12 alpha, and therefore we have alpha is equal to minus 1. Now let us compare the k components. What are the k components? K components says that 6 plus 6 alpha, right? So we have 6 plus 6 alpha is equal to, the k component is equal to 0. Therefore, we have 6 is equal to minus 6 alpha. And again, we have alpha is equal to minus 1, right? A plank with a box on it at one end is gradually raised about the other end. As the angle of inclination with the horizontal reaches 30 degrees, the box starts to slip and slides down 4 meters down the plank in 4 seconds. The coefficient of static and kinetic friction between the bus and the plank. Okay, this is such a beautiful question. If you can try to understand and analyze the question, this would make your concept regarding angle of repose, concept regarding inclination of weight on resolution of weight on inclined surface, and the coefficient and the concept of static and static and kinematic friction will be very clear with just one simple question. Okay. Well, of course, not that simple. Uh, okay. So, having said that, let us try to understand and visualize the given, the question here. So, to make this concept more clear, I'll make use of maybe 5 to 6 diagrams, and we will first try to understand what is angle of repose, and then we'll try to extrapolate the knowledge to coefficient of static and dynamic friction. Okay. Right. So let us say, okay, so let's start from a diagram here. So this is the surface, okay, and there's a plank here, okay, and an object is placed on the plank, and angle between the surface and the plank here is 0 degrees. So let me mark the forces here. So say this is normal reaction, right? And then we have this is mg cos theta, right? Now another force will act here, mg sin theta, and this is the force of friction, which is mu into n, right? So we have Fr, frictional force, is equal to mu into n. Now you may argue there is no mg sin theta here because the component is because this is not an inclined plane. It is very simple. If you substitute 0 here, it is sin 0, so mg is 0, so this component is 0. Cos theta is cos 0, which is 1, and you only have mg. So just draw the diagram for better clarity here. Why? We'll come to it. Now what we'll do is, we will now so this is the ground, right? This is the ground. So this was the ground and this is the plank. Okay. Now we have the ground here. And what has been done is that the plank is raised at an angle theta. Plank is raised at an angle theta. So what will happen to the block? This is the block, right? Let us draw the various forces here. So if we have to draw the forces, we understand that this component here would be mg sin theta, and the opposite component would be mg cos theta. The one acting upwards would be the normal reaction. The one acting downward would be, oh, I'm sorry. This is not mg cos theta. This is mu r, right? This is mu n, and what we have downwards is mg cos theta, right? Okay. Now let us go even further. So say this is the ground, right? And we raise the theta value now. We raise the theta value such that the plank is here at this position, theta value. So this is the block. Now what will happen to mg sin theta? See, the magnitude of mg sin theta will now increase, right? Magnitude of mg sin theta will now increase. Why? We'll see that. So we have mu n. Okay. Now why will magnitude of mg sin theta increase? Because as theta increases, we know that sin theta will also increase, which implies mg sine theta will also increase. So what's basically happening here is that mg sine theta component is actually trying to pull this block downwards, but it's not happening because why? Because the frictional force mu n is trying to pull it upwards. Okay. So let us draw one more diagram. Okay, maybe we need more than one diagram. So this is the ground. Now the plank is at even higher value. Don't worry, we will discuss what these values are. Theta again. Block, right? Okay, we didn't mark the forces here. So this is normal reaction, and opposite to this is mg cos theta, right? So again here, what we have here is the component of mg sin theta, which is increasing as theta increases, right? And this is mu into n, where this force is n, and the one which is acting downwards is mg cos theta. Okay. So far the body is at rest. I repeat, so far the body is at rest. Now let's see what happens when the angle becomes 30 degrees. Now let's see what happens when the angle becomes, so this is theta. Now let's see. So this is at 30 degree. Okay. Now when it is 30 degree, what we see is the block has started to slide down. So this was the initial position. Maybe this was the initial position. Okay. And the block has now started to slide down, which means the mg sin theta component here, is actually has overcome the mu n here. Okay. So this is n, this force is mg cos theta, and after some time what happens? And after some time, for this value theta is equal to 30 degrees, the block has reached the bottommost position, right? The block has reached the bottommost position, and we've been asked to find out this distance, which is s, and all of this takes place in t is equal to 4 seconds. Okay. So let us go through the question once again. See, ground, plank, and object is resting. Slowly the angle between the ground and the plank is theta. It is raised. Mg sin theta will try to pull the block downwards. Mu n will try to pull the block upwards. Here the velocity, okay, let me write down that also. So at theta is equal to 0, what is the value of velocity? Velocity is equal to 0. What is the value of acceleration? Acceleration is also equal to 0. Now, when we come to here, there is some value. Say for example, theta is equal to 10 degrees. Okay. Even when theta is 10 degree, the velocity is 0, and therefore the acceleration will also be equal to 0. Say theta is increased. Say here theta is 20 degree. Now when theta is 20 degree, we know that the mg sin theta component is larger, and therefore the body will try to come down. But now, according to the question, is the body coming down? No. Which means the mg sin theta component is still being opposed by mu n, which means velocity here will still be equal to 0, and acceleration will definitely be equal to 0, right? So we have theta is equal to 0. Sorry, theta is equal to 0, velocity is 0, theta is equal to 10, velocity is 0, theta is equal to 20, velocity is 0. Now, let us say theta is equal to 25 degrees. 25 degrees. Again, velocity here is equal to 0 and acceleration is 0. Why? Because the question says that it reaches 30 degree. So theta is 25, which is less than 30, and therefore the block is still at rest, and mg sin theta component is still being balanced by mu n. But what's important to understand is that as soon as theta becomes 30 degree, see, this is where the observation starts to originate. So we have t is equal to 0 here. The block has been now under observation. The motion is now under observation. And what do we see? What we see is that there is some velocity that is obtained by the body, right? There is some velocity obtained. Let us say that velocity is x meter per second. Okay. So here the body at this position, the velocity, initial velocity is 0, and the body has now started to attain some velocity, which is x meter per second. But yes, the acceleration is still 0 now. It will slow, it will keep on increasing. Now, as the block slides down, it will eventually reach the surface. And when it reaches the surface, it is given the question that the final velocity is 4 meter per second, and the time taken for this travel is 4 seconds. And we've been asked to find out this horizontal distance traversed by the, so this distance traversed by the body. Okay, so that's what we need to find out. See, no matter how hard I try to explain you this, unless and until you try to draw this on your own, okay, you try to draw this on your own, and if you try to explain yourself the concept, things will become more clear only then. Okay, so I would suggest that you try drawing it on your own. If you have any doubts, feel free to ask me after the class, and those who are watching it online, please make sure they post in the comment box. If you want, we can have a detailed review of this question again, because this is a very important question. Why is it important? I told you two reasons. One, because it will help you in understanding the resolution of the components of weight in an inclined plane. Second, this will help you understanding the coefficient of static and kinematic friction. Now, that is where this question now becomes interesting. See, if we were to understand static and dynamic, or say static and kinematic friction directly, we just use simple logic behind it. What is it? It is static friction as long as the body is at rest. It is kinetic friction. Oh, let's say kinematic. My bad. So it's kinetic friction. It's kinetic friction as soon as the body is in motion. So if you to understand the friction here, what would be the friction here? Here mu would actually be equal to mu s. Why? Because the body is still not moving. Here the mu is mu s. Why? Because the velocity is 0. The velocity is 0 again. So here it is, instead of mu n, it is actually mu s into n. So theta is equal to 25. What will be mu n? It will be mu s into n. Why? Because the velocity is still 0. But if the moment it starts sliding, there is some amount of velocity. Therefore, mu here is not mu s. Instead, it is mu k. Right? So look at one figure. See, this one figure, we just arrive at two different frictions. One is static and the other is kinetic friction. And again, here also throughout the motion, the friction is kinetic, mu k. And what have we been asked to find out? The coefficients of static and kinetic friction. Right? So, which we will find out using these two diagrams. Okay? So we'll use this diagram for kinetic static friction, and we'll use this one for the kinematic friction. Let us take both of them one by one. Okay. So what we'll do is we'll draw both of them one more time for better clarity. So let us say this is the ground, right? And this is the plank. This is for some value theta. Now, at theta is equal to 30 degrees, the object is still at rest, but it just started to move, right? It has just started to move. It has not in motion. It just started to move. So up to 30 degree, what happens is the block remains at rest. So at theta is equal to 30. Let us draw the various forces here. So with the block, weight is acting downwards. This is mg. Can be resolved into two components, mg cos theta. See, how to resolve it, we have discussed in detail. Maybe for those who are watching it online, I'll post the video link somewhere over here. Please do watch that. So this is mg sine theta. And this component here is mg cos theta. Normal force is always perpendicular to the contact surface. The contact surface is this. Therefore, this is the contact force perpendicular to it. Okay. And frictional force will be Fr is equal to mu into n. And from our discussion earlier, we know that which mu is this? Is it static or kinetic? This is static because the body is still at, the block is still at rest. So the block is still at rest. Okay. Now what we'll do is we'll try to write the equations of motion. So since it is rest, we can say that sigma fx is equal to 0. And we can say that sigma fy is also equal to 0. Since sigma fx is equal to 0, what can we say? We can write here that mg sine theta is equal to mu into n, which mu? This is mu s, right? Now, when we have sigma Fy is equal to 0, the only normal force upward direction is n, and the one acting in the downward direction is mg cos theta, right? So, if we bring up this equation, n is equal to mg sine theta, and if we substitute that over here, what do we get? What we get is mg into sine theta is equal to mu. Which mu? What we have here is mu static into, instead of n, what we have here is m into g into cos theta, right? So m by m is 1, g by g is 1. So what we get is sine theta upon cos theta is equal to mu. Which mu? Mu static, and therefore tan theta is equal to mu static. What is theta? The value of 30. So mu s is equal to tan 30, which is tan 30 is 1 by root 3, which is 1 by 1.7, right? So this becomes 10 by 17, 100 by 17, 5 8 85, so somewhere around 0.5. Okay, so the coefficient of static friction is mu s is equal to 0.5 is what we get. So coefficient of static we decided to be 0.5. Now let us see what happens in the case of kinetic friction. So again the same figure. We have the ground. Okay, maybe we use tool diagrams here. $30 degrees. So say this is at t is equal to 0, and this is at t is equal to 4 seconds. So at t is equal to 0, the object was, or the block was here, and at t is equal to 4 seconds, the object slides down and reaches here, right? What are the various forces acting on it? We know that this force here would be mg sine theta. This force here acting would be mu into n, right? This is n, and this is mg cos theta, right? And what we are trying to find out is this distance s. Okay, right. So how do we do this? And the velocity is also given. Velocity is going to be 4 meters per second, and the initial velocity, the object is still at rest, so it is u is equal to 0, right? Okay. So after the body is sliding, this will be replaced by mu k and not mu s anymore, because the object is now started to move, right? It has started to move from rest, but it has it has a tendency of moving, and therefore coefficient of friction is now kinetic in nature. Okay. Now let us find out the equation that we need to use here. See, we know that s is equal to ut plus, right? Ut plus half at square, and along the x direction this would be sx is equal to ux into t plus, right? Ux into 2 plus half into ax into t square. Why am I taking ax x direction? See, look at the diagram here. Is there any motion along the y direction? Is there any motion along the y direction? No. The object is only sliding downwards, which means the object is having only a x component. Motion along the x component. There is no motion along the y component. Now, according to the question, right? According to the question. Oh, wait. I think okay, it is given that it slides 4 meters, right? We're going to find out the coefficient of friction. Okay. So what we have here is s is already given to us. S is given to us as 4 meters. So actually sx is 4 meters is equal to, what is ux? It is 0. Why? Because the object is initially at rest, into t plus half into ax into, what is t square? It is 4 seconds to complete the motion, so this is 4 square. So we have 4 is equal to a by 2 into 4 square, right? So this would be 4 into 2 is 8. So 8 is equal to a into 4 square. 4 square is 16. 16 by 8 is, so 1 by 2 is equal to a. Oh, when I say a, it is ax. So ax is half is what we get. Ax is equal to half is what we get here. Now what we need to do is we need to find out the value of ax. Let us see how. See, for the motion along x-axis, alone, we have sigma fy is equal to 0 and we have sigma fx is equal to m into acceleration component along the x-axis, right? Now what is sigma fy is equal to 0? See, if you understand from the figure here, there are only two forces acting, which is n acting here. N is equal to m into g into cos theta, right? Mg cos theta. And what are the x direction forces along the x direction? We have mg sine theta. So sigma fx would be, what is the net direction of motion? The net direction of motion is acting downwards. The net direction of motion acting downwards, which means all those forces which are acting along the net direction of motion would be taken as positive. I repeat, which means all the forces which are acting along the net direction of motion will be taken as positive, and therefore we take plus mg sine theta minus all the forces which are acting against the direction of motion. Direction of motion is towards downwards, but mu into n is acting upwards, which means that will be taken as negative. Minus mu into n will be equal to m into ax, right? Okay, so now what we get is mg sine theta minus mu into, instead of n we can write mg cos theta. So mu into mg cos theta is equal to m into ax. If you divide the entire equation by m, what do we get? What you get is g into sine theta minus mu into g into g into cos theta, m by m is 1, is equal to ax, right? Now again, what is g here? With g we're talking, sorry, what is mu here? It is mu kinetic. So this is the value of a, right? This value of a. So we got the value of a. But what is the value of ax otherwise? Ax we have found it to be 1 by 2. So now we'll substitute this as 1 by 2. So we can write that g into sine theta minus mu kinetic into g cos theta is equal to 1 by 2. Now what is the value of g? 10 into sine theta is sine 30 minus mu k, we don't know, mu k, into g is 10 into cos 30 is equal to 1 by 2, right? Okay, so this becomes 10 into sine 30 is 1 by 2 minus mu k into 10 into, what is cos 30? Cos 30 is root 3 by 2, which is equal to 1 by 2. So if you can eliminate 2 from entire equation, 2 will be eliminated. So what we get now is a linear equation which says 10, right? Which says 10 minus mu k into 10 into root 3 is equal to 1, right? So we have 10 minus 1 is equal to mu k into 10 root 3. Therefore 9 by, right, 9 by root 3 into 10 is equal to mu k. So if you cancel this, what do we get? Mu k would be equal to, multiply 9 by root 3 on both sides. Sorry, multiply root 3 on both sides. What do you get? Multiply root 3 on both sides. So what we get is 9 into root 3 by root 3 into 3 is 3. 3 into 10 is 30. So cancel this 3 tens. You get is 3. So what you get is 3 root 3 upon 10. 3 root 3 upon 10, which is 3 into 1.7 upon 10. 1.3 is 51. So 5.1 by 5.1 by 10, what you get is equal to 0.51, right? This is 5.1. Now I think we are a bit getting confused with the value of static friction, which is also what you get is 0.5, right? Let us go back to the options. Options is 0.6 and 0.5, so we are in nearby values, so we can't skip the calculation. We need to do it thoroughly here. So it's 10 by 17, right? So if we try 10 by 17, let us find out 10 by 17. So if we're 10 by 17, right? So it's 0, 0 0.5, 85, right? 15, 10, 17 into 8, 7 8s are 56, 8 1s are 13, 136. Yeah, so what you get is 0.58, right? So it is 0.58, which can be approximated to be 0.6. Yeah, that's what we skipped. So we have mu static is equal to 0.6, and what is the value here? Mu kinematic is equal to 0.5, and mu static is equal to 0.6, right? So these are the values. Let us finalize it. Do we have the options? Yeah, so it is static and kinetic. Static is 0.6 and kinetic is 0.5. Okay, so that's it with this question. I would say it's a really important question. In fact, it covers almost every every possible content of friction. It covers kinetic friction, it covers static friction, it covers the equations of motion, it covers the direction of friction, it covers in resolution of weight on an inclined surface. So overall a really good question. Okay, so having said that, let us move on to the next question, which actually is again based on a free body diagram of pulley block system. Let us go to that. A block A of mass M1 rests on a horizontal table. A light string connected to it passes over a frictionless pulley at the edge of the table, and from its other end, another block of mass M2 is suspended. The coefficient of kinetic friction between the block is mu k. When the block A is sliding on the table, the tension in the string is. This is one such question where students often get confused, not because the question is difficult, but because of the fact that there is no diagram given. So let us see how to do that. Let us see how to overcome that. So find out what's given in the question. It says the edge of a table, right? So we have edge of a table, and what is present here? A pulley is present here, right? And the frictionless rope or a frictionless string is passing through it. At one end of the string, we have a block of mass m1. At the other end, we have a block of mass. M2. Okay, and it is given that the block A is sliding on the table, which means the block A is moving like this towards the left, which means M2 would be moving towards the vertically downward direction. It's also given that there is kinetic friction. So say there's friction in this table here, and the coefficient of kinetic friction is given to be mu k. Alright, it's a very simple question. Let us first try to understand the question in two different components for block M1 and for block M2. Okay, which will make our understanding even more better. So let us first write down for the block M1. For the block M1. Now for the block M1, what I'll do is I'll draw the diagram one more time. So this is M1. What do we write first? We draw the net direction of motion, which is towards the left. And we know that if there is an object placed on the surface, it will experience a weight. Normal reaction would be acting against the body. right? Sorry, against the will be acting the perpendicular direction against the surface of contact. Now, since there's a string connected here, the tension will be acting away from the point of contact on the surface. So this will make it tension, right? And since the net direction movement is towards the left, we can say that there is friction. There is friction that is acting towards the right. Okay. So there's friction acting towards the right. Okay. In which case, is there any movement for the mass m1? Is there any movement for the mass m1 towards the vertical up direction? No. Is there any movement for the mass m1 towards the vertically downward direction? No. The mass m1 is moving only along the surface. It is sliding along the surface, which means that for this body, sigma fy is equal to 0, and we can say that sigma fx has an acceleration which will be equal to m1 into a, right? Now what does it mean sigma fy is equal to 0? See, look at the forces which are acting in the y direction, n and m1g, which means n vertically upwards will be compensating m1g vertically downwards. Sigma fy vertical direction, sigma means sum, so n in the vertically upward direction would be balanced by m1 in the vertically downward direction. So we can write here that n is equal to m1 into g. Now what about sigma fx? See, I'll make this concept one more time very clear to you. This is the net direction of motion, which is towards the left, right? And what's happening here? Tension is acting along the direction of motion, right? So this is f net, and tension is acting along the direction of motion. One more time. This is the direction of motion, and where is friction acting? Friction is acting opposed to it. Now, when both the forces are in the same direction, what we do is we usually consider this to be positive and fr to be negative. So when we write sigma fx, what we'll do is we'll write it as positive t minus fr is equal to m1 into a, right? Now what is fr? Fr we know is mu into n, which is equal to ma. M1A. Now, which mu are you talking about? Is it static or kinematic? Sorry, is it a static or kinetic friction? Since the body is sliding, it definitely means that this friction is kinetic in nature. So it is T minus mu k into n. What is n? From this equation, we have n is equal to m1g is equal to m1 into a. So this is our first equation. Now, since there are two bodies, definitely there should be another equation as well, right? So let us write down that equation also. So to write down that equation, we'll redraw the figure one more time. So this was the table, right? Pulley. I'm not considering the other diagram now. I'm considering only the body which is hanging downwards. The mass of the hanging downward body is m2. We know that it will experience a force m2g acting downwards, right? Definitely there will be tension in the string here. It will originate from this point and it will be against the point of contact. So we have tension T in the string here. This body has no horizontal direction movement, horizontal direction. It will move only in the vertical direction, which means for this body we can write that sigma fx is equal to m2 into a, whereas sigma fx is equal to 0, whereas sigma fy here would be equal to m2 into a. Now what is sigma fy? Let us go to the concept one more time. So net direction of force is acting downwards because the body is moving downwards. Therefore the net direction is towards vertically down, and tension is acting in the opposite direction. One more time. Net direction of motion is acting downwards, whereas weight is also acting downwards. So since they are acting in the same direction, we'll consider weight to be positive. So we consider We'll consider weight to be positive. Since tension is acting against the direction of motion, we'll consider tension to be negative. So when we write sigma Fy, how can we write this equation as? We'll write this as plus m2g, right? Plus m2g minus tension is equal to m2a. So we got one more equation. Two bodies, two equations. Let us find out, would it be able to solve for the unknown? Let us see. So what is equation number one? Equation number one is t minus mu k into m1g is equal to m1 into a, and the other equation is, say, minus t plus m2g is equal to m2a. Now what I'll do is I'll subtract equation 2 from 1. So this is 1, this is 2. So I'll subtract, or I'll say I'll do 1 minus 2. So what do I get? T minus mu k into m1 into g. Now doing minus, right? Minus within bracket we have minus 2 plus m2 into g is equal to m1 into a minus m2 into a, right? So this will become t minus mu k into m1 into g. Minus into minus is plus, so we have plus t minus m2g is equal to m1a minus m2a, right? Okay. Now, now t plus t is 2t. So what we get is 2t minus mu k into m1g minus m2g is equal to m1a minus m2a, right? So at this point, could we find the rest of the answer? No, we can't. Why? Because there is a again left here. Right. So we need to find out the value of a. Okay, so in which case, what we'll do is we will, instead of finding 1 minus 2 here, what we'll do is we'll find a 1 plus 2. So what do we get? What we get is t minus mu k into m1g plus it is, right? So plus into minus is minus t plus m2g is equal to m1a plus m2a. And now what happens? Right, so t minus t is 0 now. So what we get is m2g minus mu k into m1g is equal to a into m1 plus m2. Okay, so what is a from here? A is m2g minus mu k into m1 into g, the whole upon m1 plus m2. Let me highlight this for you. So this is the value of a. But are we done with the question? No. Why? Because we've been asked to find out the tension in the string and not the acceleration. How do we do that? Let us bring equation number 2 here. What is equation number 2? Equation number 2 says that minus 2 plus m2 into g is equal to m2 into a, right? So I can write this minus t. Okay, let us make it plus t. So we can write that m2 into g minus m2 into a is equal to plus t, right? So m2 into g minus a is equal to t, or m2 into g minus a. What is the value of a? We have a here, so we'll bring a here, which will give it as a is m2g, right? A is m2g minus mu k into m1g. So it is minus, right? So we'll keep this entire into bracket. The whole divided by m1 plus m2 into m plus m2. Okay. And this whole is equal to T. Now, what we'll do is we'll keep M2 here. We multiply this. So what we get is GM1 plus GM2 minus M2G minus mu K M1G the whole upon M1 plus M2 is equal to T, right? So if you can observe here, GM2 minus GM2 is 0. And next what we have is M2 can be multiplied inside. So what we get is G into M1 into M2 minus mu K into, right, minus mu K into M1 into M2 into G, the whole divided by M1 plus M2 is equal to T. Maybe you can take M1 M2 into G common here. So we write M1 M2 into G is common as 1 minus, right, which will give us as 1 minus what is left, 1 minus, oh wait, there is a minor mistake here, right? Why? Because we are multiplying this minus inside, so this should become positive. So this is positive 1 plus mu K the whole upon M1 plus M2 is equal to T. So this will be our final answer. Okay, so let us go through the entire problem one more time. So we got the question without the diagram. We first drew the diagram, right? And then what did we do here? We first solved the diagram for M1 alone. M1, net direction towards the left, friction towards the right. Tension is along the net direction of motion, so it is positive. Friction is against the net direction of motion, so it is negative. We wrote sigma fx. We know that sigma fy is equal to 0. Then what did we do? Then we came to the second set of diagram where we considered M2 acting downwards, net direction moving downwards, so weight is positive, tension is against the direction of motion, so tension is negative. We wrote one equation. Then what did we do? We solved these equations simultaneously to obtain the value of acceleration. Then we substituted the value of acceleration back in equation number 2 to find out the value of T, right? So yes, see, these kind of questions become easy for me because I practice this for a longer period of time. So for those people, for those students, I would say who are doing it for the first time, you may find it difficult, and the key to overcome that difficulty is to practice more. Right? The more and more you practice, the better you become at solving problems. So this is one such question where the figure was not given. Well, we have a similar question, not using the pulley rope system, but a very similar question to find out the force and these kind of values. But here, unlike this one, we have a given figure. So here again, the next question we'll draw free body diagram and try to solve these. So do solve this question on your own one time, right? Take some time. Don't copy down the question. Take some time. Try to solve it on your own. Come back to the question. Come back to the solution if you find any difficulty, and clear the difficulty. If you have any doubt, please feel free to ask me. Our students watching it online, please make sure that you feel free to write to us. We'll definitely get back to you. And once you're done solving this question, maybe what you can do is you can go to the next question and try solving it. If not, if you're not confident in this question, please do this. Do solve this question one more time, which will increase your confidence level. Having said that, let's move on to the next question, which is question number 10. Three blocks A, B, and C of masses 4 kg, 2 kg, and 1 kg respectively are in contact on a frictionless surface. If a force of 40 Newton is applied to the 4 kg block, then the contact force between A and B is, because this is a really good question. Let's see how to solve this. So first what I'll do is I'll draw the combined diagram here, which means I'll select all the three masses together and name them A plus B plus C, right? The complete mass A plus B plus C, and then analyze what are the various forces acting on it. So the first force acting on it is F external, right? Is F external, and the body will experience a movement in the positive x-axis, right? So if we have to write the Newton's laws of motion here, third law of motion, what do we write here? We can write that F external, right? F external would be equal to mass into net acceleration, right? Or we can write that F is equal to, in easier way, we can write F is equal to ma. And what is F? It is given that 14 Newton. So it is 14 Newton. And mass, what is mass is equal to? So it is 4 plus 2 plus 1, right? So we have 4 kilogram plus 2 kilogram plus 1 kilogram. So mass is actually 7 kilogram into acceleration. And therefore acceleration is 14 by 7, which is 2. So we have acceleration is 2 meter per second square, right? Acceleration is 2 meter per second square. Now let us see the case between A and B. So the contact force between A and B is, okay. So let us draw the diagram for A and B. So this is figure A, right? Now what I'll do is, now I'll draw these bodies separately so as to explain what happens when they come into contact, okay? See, now when you push A will come in contact with B. Most of the students get a confusion here regarding how to draw the normal reaction. We'll come to that. So see, this was the case earlier. Okay, this was the case earlier, and what happens is, when F external is given, right? When if external is given, A comes and collides with B. Okay, A comes and collides with B, and give me a second. Say this is what we get. Okay, so the distance between them is reduced. Now A and B are moving together is what we visualize here. So if you break this visualization into two parts, let us see those two parts simultaneously. So A is colliding on B, which means A will give a force on B, right? Let us call this force as the normal reaction. And this normal reaction, we'll have to write it in detail so to understand to get the concept very clearly. So this is normal reaction on B due to A. Okay. Now by Newton's third law of motion, an equal and opposite force will be given on A, right? So if we mark that force, we can write like this. This is normal reaction acting on A, right? Normal reaction acting on A due to B. Okay. Now, if we take the free body diagram of A alone, let us see the various forces acting on it. Let us see the various forces acting on A. So for the body A, right? For the body A, okay, let us try to even more simplify this. So let us draw the diagrams. Sorry, let us draw the forces acting on A alone. See, the first force acting on A is normal reaction, right, from the surface. Normal reaction on A from the surface. And then we have weight acting downwards. So weight acting downwards, right? A mass of A acting downwards. And then we have the F external here. F external. And now what did we see? We saw that there is another force, normal reaction on, contact force, right? Normal reaction on A, which is happening due to B. Okay, so this is the condition for, these are the forces acting for the block A. Now let's see, is there any vertical motion? No vertical motion, right? So there is no vertical motion. Now if there is no vertical motion, what does it implies? This implies that sigma Fy is equal to 0. And if sigma Fy is equal to 0, it implies that forces along the positive Y would be equal to forces along the negative y. Therefore, we can say that normal reaction on A due to surface is equal to MA into G, right? But what will be the condition for horizontal motion? Horizontal motion condition will be sigma fx is equal to m times a net, right? And what is a net? We derived a net to be a is equal to 12. So here we can write that this is mass, okay, not mx, it should be ma. So this is ma. What is the value of ma? Mass of ma is 4 kilograms. So we have 4 into what is a net? A net is 2. Now what is sigma fx? See, what is the net direction of motion? Net direction of motion is towards the right, right? Net direction of motion is towards the right. So we'll draw the net direction of motion first. Net direction of motion is towards right. Again, net direction of motion is towards the right. Where is F external acting? F external is acting towards it. So F external and the direction of motion are in the same direction. But where is normal reaction acting? Normal reaction on A due to B is acting in the opposite direction, which means we'll take F external to be positive and net external to be normal reaction on A to be negative. In which case, what would be sigma fx? Sigma fx would be positive F external minus normal reaction on A due to B, which is actually the force acting between A and B. So what is force external? Force external is 14 Newton, right? 14 Newton minus NAB is equal to 4 into 2 is equal to 8. Therefore, 14 minus 8, 6 is equal to normal reaction on A due to B. Well, see, I think I'm taking longer than usual to solve these questions. Usually, you don't get the luxury of time to solve this question in such a detailed way. But again, it's just the reason to explain this much is to make sure that you understand the concept behind every every free body diagram of the given block. So what I would suggest is you can try doing the same question. But this time using the block B. So we have, how do we do that? We draw the combined figure once, right? And then we, instead of taking A, we take B. And then we understand the various forces acting on B. We draw the effect of F external, the effect of normal reaction on B due to A. And then let's find out what are the, what would be the value of NAB if you do so. So try doing it, get back to us. And after doing that, we'll move on to the next question. Okay, now this time we have a question based on law of conservation of momentum. Let's go to that. Mass 10 grams moving horizontal with a velocity of 400 meters strikes a wooden block of mass 2 kilogram, which is suspended by light inextensible string of length 5 meter. As a result, the center of gravity of the block found to raise a vertical distance of 10 centimeter. The speed of the bullet after it emerges horizontally from the block will be. See, first of all, let me just give you a brief introduction to what this question is. This actually is a question based on the concept of ballistic pendulum, which is actually used to determine the velocity of projection, or the velocity of or say initial velocity of projection, ballistic pendulum. So what we'll do is we'll try to first understand what this ballistic pendulum is, and then we'll try to come back to the question. Okay, so give me a minute. Let me write down some of the basic theories associated with ballistic pendulum, and then we'll come back to the discussion. Okay, so now see, I would suggest you make a note of this first, right? You make a note of this, and we'll I'll tell you which application is important here and which is not. So bullet embedded in the block is actually the most important point when it comes specifically to ballistic pendulum. But the question here asked is not embedded in the block. It is when the bullet is emerging out of the block. So I would say when the topic of ballistic pendulum is really important, especially for the JEE mains. This is surprising that such a question came for the NEET exam. But when it comes to JEE mains, definitely bullet embedded in the block is important. But since it's been asked in the NEET exam, we will come across this question also, bullet emerging out of the block. Okay. So what is ballistic pendulum? Is a mechanism used to find out experimental mechanism used to find out the velocity of projection. Okay. So there are two cases. One in which a bullet is embedded in the block, the other when the bullet emerges out of the block. So when the bullet is embedded in the block, we divide this topic into two subhalves. One when the bullet hits the block, the second when the bullet and the block swings to the maximum position. I repeat, bullet hitting the block, bullet plus block swinging to the maximum position. In the second part, which is actually the question here, bullet hits the block, it penetrates, it makes a bore or it makes a hole and then exits the block. And the second part, instead of bullet plus block swinging, here only the block will swing to the extreme position. Okay, so ballistic pendulum embedded in the block, emerging out of the block. Embedded hitting the block first, then bullet plus block swinging to the maximum position. Emerging out, bullet hitting the block first, then block only swings to the extreme position. Okay, yes, I've not drawn the diagram, we have not done the visualization yet, so there might be confusion while you read this. So now what I'm going to do is I'll take all these steps. So this is 1.1, this is 1.2, right? And then we'll discuss 2.1 and 2.2 in detail, and I assure you, you will be able to solve any question from ballistic pendulum after this discussion. Okay, so let's start with 1.1. So now we'll see the earlier point, what we said as 1.1 and 1.2 is, see, so we'll divide ballistic pendulum problem into two different halves. One, where the bullet which actually comes from the gun. So there's a bullet which is coming from the gun. Okay, so this bullet, what will it do? This bullet will hit the block, penetrate the block, and it will stay inside the block. And when it hits, what happens? When it hits, due to this penetration, some velocity is transferred to the block, and the block will now get some velocity, as a result of which the block will start swinging, and eventually the bullet remains inside the block like this. Okay, so we'll discuss in two halves. One, where the bullet is actually hitting the block. Two, where the bullet plus block is actually being displaced from the initial position to the extreme position. Okay, so block to block plus bullet hitting the block, bullet plus block reaching the extreme position will be the swinging portion that we'll discuss the second part. Okay, so let me just give you a brief intro of what we are going to discuss here. So this hitting the block, this much portion will apply. Okay, now for that matter, we'll apply conservation theorem in both. But the first half, what is conserved? Conservation of momentum takes place. And second half, what is conserved? Conservation of mechanical energy takes place. Okay, why not? We'll discuss the next section. So give me 5 more minutes. I'll just write down the next one and then we'll resume. Okay, so we'll discuss now hitting a bullet hitting the block. Okay. Okay, so done writing here. So now we will discuss the first part of the problem, where the bullet is actually hitting the block. Okay. Now see, let's try to pay our maximum attention and try to understand what's given here. So this is a ceiling. A string is holding a block. Now we are considering the block and the bullet as a system. Okay, so what is system here? The block and the bullet. And when block and the bullet is the system, what we can say is that net external force acting on this system is equal to 0. What do we consider as block? What do we consider as a system? Bullet and the block. And when bullet and the block is considered as a system, what can we say? We can say that the net external force acting on the system is equal to 0 because there is no other force acting on it, right? Okay. Now in this case, if the net external force acting on the system is equal to 0, what can we say? We can say that the momentum is conserved, right? Therefore, momentum initial should be equal to momentum final, right? Now, another way of looking at this is when the bullet hits the block, this will make a hole in the block, right? And the block and the bullet is getting embedded in the block. So when the bullet hits the block, it will make a hole. So just to put the diagram, I'm just trying to make more sense here. So here, when the bullet, it makes a hole here, and then it gets embedded within this block, right? And now the bullet and block will together act as a body. The bullet and block will together act as a body. Now when bullet is entering the block, and when it is getting embedded in it, we can say that some energy of the kinetic energy obtained by the bullet when it was fired from the gun, some of the energy is lost in many ways, maybe as sound, or maybe as some energy to to bore this, some energy to cut these wooden fibers, or maybe some energy to pierce into these fibers. So there can be many different ways here. So energy is lost in many such ways. And since energy is lost in many such ways, we can say that this collision is definitely inelastic collision, in which case what can we infer? That the momentum initial is equal to momentum final. And if we were to assign numbers for the bullet as 1, for the block as 2, for the bullet as 1, for the block as 2, how can we write the momentum? We can say that initial momentum is m1 u1 plus m2 u2, and the final momentum is m1 v1 plus m2 v2. But there is a difference. Why? Because the bullet and the block are acting together, are now existing together, which means this will be replaced by m1 plus m2 having a common final velocity v2. Is the concept. So if we were to equate this equation, what do we get? M1 u1 plus, right? M1 u1 plus m2 u2 is equal to m1 plus m2 into v2. Therefore, what does v2 represent? v2 represents the velocity of the block, which is equal to, right? Which is equal to, oh, one more thing. What is say, since this block is initially at rest, what is the value of u2? That will be equal to 0, which means this entire term will now, vanish, and all what you get is v2 is equal to m1 upon m1 plus m2, the whole times u1, right? So this is the first part, bullet hitting the block. Now what will we do? Now we'll go to the next part, which is so bullet hitting the block we did. Now what we'll do? We'll now see the swinging of the block. Block plus bullet will now swing to the extreme position. Let's see that now. So we discussed the first part of the problem, wherein we were talking about the bullet being hitting the block. Now let us see what happens when the bullet and the block is swinging to the extreme position. So bullet is entered the block, right? The bullet has penetrated the block, and the block is now going to swing with the bullet. So this is the initial position, right? This is the initial position. Bullet is there. The only force acting here would be tension, and since the bullet has entered into the block, there will be some resistive forces. Let us not discuss that here. We are neglecting that. Now, when the pendulum is swinging like this, when I say pendulum, this string with the bullet block, when it is swinging like this, eventually what will happen is that the block will reach a point which is the extreme position. So if we have to consider the movement of this pendulum from position A to position B, right? It swings from A to B, and then B will be the extreme position. And we know when an object in pendulum is in the extreme position, what happens to the velocity? The velocity at that extreme position is equal to 0. So at B, VB is equal to 0, and at A, what is the velocity? C. Exactly. At A, the initial velocity, the velocity at A is actually the velocity that we calculated earlier, which is nothing but V2. And what is the expression for V2? We wrote it earlier that V2 is M1 by M1 plus M2 times U1, right? It is the same velocity with the block we'll have here. But as soon as the block reaches the position B, the velocity will become 0. Now, during this motion, we know that it is not just tension, but another force comes into picture, which is which is the weight of the body. Now, weight of the body is caused due to the gravitational force, which is actually a conservative force, which means this overall motion of bullet plus block swinging to the extreme position is actually under the influence of a conservative force. And when such a motion is under the influence of a conservative force, what can we say? We can say that the mechanical energy is conserved. And mechanical energy is conserved means mechanical energy at A should be equal to mechanical energy at B, which means kinetic energy at A plus potential energy at A should be equal to kinetic energy at B plus potential energy at B, which further gives us half m into v at a square plus m into g into h of a is equal to half m into vb square plus m into g into h at b. Now look at what things get cancelled off. See, h at a, if you consider this as a reference ground, which means this object is present exactly in the reference ground, therefore ha is equal to 0, right? Therefore we can write ha is equal to 0. Now, if we consider, see, already we have VB is equal to 0 here, so this term will also get eliminated, right? And only difference here is that since the body comes to this height, the only new variable here is h. So HB can be written as, HB can actually be written as h. And therefore we can say that, half m into VA square is equal to mg into HB. And therefore VA square is actually equal to root of, so m and m will cancel. So what we get is, will be equal to root of, oh, well, I made a mistake here. This should be m plus m, right? Yeah, because it's potential energy of both. So it should be m plus m, should be m plus m, should be m plus m, and all those terms will cancel off. And what we get is mg into hb, right? Mg into hb. So m and m will cancel here also. M and m will now cancel here. So, sorry. So m and m will cancel here. What we'll get is VA square is equal to root of 2g into h, and therefore VA is equal to root of 2gh. But what is VA? VA is equal to V2, right? VA is equal to V2. Therefore, we can write that m1 by m1 plus m2 times u1 is equal to root of 2gh. See, with this equation, you'll be able to find out any unknown variable. Okay. Now, we're not done with the problem yet. In fact, we're not entered it. Why? Because so far we're discussing only about the bullet and the block embedded in it. Now, what comes next? What comes next is the true problem here. So, which is actually the case when the bullet, instead of getting embedded, it emerges out of the block. So now we'll discuss bullet hitting the block and bullet swinging to the extreme position as 2.1 and 2.2. So now I think there's not much detailing required, right? We just go directly in the equation. So give me a minute, I'll write down things. In the meanwhile, you can try writing down the equation on your own. Okay? And let's catch up after a minute. Now, those who have paid much attention to the first case, you'll be able to write these equations very very fastly. Now, those who are watching it online, if you have any doubt in this, in this section here, I would request that you please pause the video, go back to the discussion on bullet being embedded and not being emerging out. Watch that discussion one more time, make a note of it, write down it on your own, then come back to this. Things will become more clear then. Okay. Now here what we have is the bullet is hitting the block, and then the block is begin to displaced, and the bullet emerges out of the block. Of course, to make more sense, let us say that there is a hole in the bullet now. Sorry, the hole in the block now, and the bullet is out, right? Okay, now again, the same concept repeats. Collision is inelastic, and the momentum is conserved. And if you consider this complete system, bullet and the block as a system, is there any other force acting on it? No. Therefore, we can say that the net external force acting on this is equal to 0. Now, if momentum initial is equal to momentum final, we have written the initial condition here before hitting the block, after final condition after hitting the block. Therefore, we can write down the momentum equation, which would be m1 u1 plus So we have 1 for the bullet, right, and 2 for the block. So m1 u1 plus m2 u2 is equal to m1 v1, this time not m1 plus m2, this time individual components, m1 v1 plus m2 v2, right? Okay, now yeah, so now what we'll do is, we know that u2 is equal to 0, right? Why? Because the block is initially at rest. The block is at rest, and therefore u2 is equal to 0. So we can write this equation as m1 u1 is equal to m1 into v1 plus m1 into v1 plus m2 into v2. Okay, now right, so this is equation number 1. Do we have any known parameters? No, we don't have any parameters here. So now what we'll do is we'll discuss the second part, which is swinging of the block without the bullet. Okay, so give me a minute time again. I'll write down things and I'll get back to you. So now we have the final part of actually we are finally entering into the question now. So now the bullet emerges out of the block and the block swings to the extreme position. So bullet is emerging out and the block is going to swing from the initial position to the final position. Initial position being labeled as A and the final position being labeled as B. We know that velocity at A is actually v2, what is v2? So v2 is what we derived from here, right? From this expression, what we get is v2. And with that velocity, the block will start to swing, and as it swings, right? So it will start with velocity v2, and eventually as it reaches the maximum position, the velocity at B will become 0. And how is this velocity decreasing? Because the motion is under the influence of gravity, and gravity will therefore pull down this block, and therefore the gravity will reduce the velocity of this block, which is actually a conservative force. And under the influence of conservative force, we know that mechanical energy remains conserved. Therefore we can say that mechanical energy at A should be equal to mechanical energy at B, which gives us the next equation, half mva square plus m into g into ha is equal to half mvb square plus m into g into hp, right? Now we know that at A, what is VA? At A, we know that VA is actually V2, right? So VA is V2, so it is V2 square plus. Now this is the ground reference, and A is actually in the same ground reference, which means there is no height here. Therefore we can say that this term is equal to 0, and this is equal to, we know that VB is equal to 0, VB extreme position, VB is equal to 0, and therefore we can say that this term also becomes 0, and what we have is mg into hp, which gives us v2 square is equal to m into g into hb, and m and m will cancel. So what we get is v2 square is equal to, v2 square is equal to 2 by 2 here, right? So v2 square is equal to 2 into gh, and therefore v2 is equal to root of 2gh, right? Okay, now what I'll do is I'll write this equation v2 is equal to root of 2gh separately over here. Okay, so we have, I'll write it over here. So v2 is equal to root of 2gh. Okay, so that's there. Now we need this equation as well, which is m1 u1 plus m1 v1 plus m2 v2, this equation. So okay, I have got the question also. So we have v2 is equal to root of 2gh, and what's the first equation? The first equation is m1 u1, right? m1 u1 is equal to m2 v2 plus m1 v1, right? Okay, so What is 1 and 2 represent here? See, one represents the bullet, and 2 represents the block, right? Okay, so we need M1 V1. So we need M1 M2 U1 U2 V1 and V2, right? So wait, are we missing any terminology here? So M1 U1 plus M2 U2 is equal to M1 V1 plus, right? Okay. So we know that U2 is equal to 0. Why? Because the block is at rest. What is the value of V2? We have it that from the equation that V2 is equal to root of 2GH. What is M1? See, M1 is given to us as 10 grams, right? So 10 grams is 10 by 1000, which is 1 by 100, so which is 10 to the power minus 2 grams. So it is 10 to the power minus 2 kilograms, right? What is U1? It is moving with the velocity of 400 meter per second. So U1 is 400 meter per second. And what is V1? The speed of the bullet after it emerges. So that is what we need to find out. So we need to find out V1. What is M2? M2 is given to us as 2 kilogram, right? It is given to us as 2 kilogram. So if we had to write, substitute these things in the equation here. M1 into U1. So M1 is 10 to the power minus 2 into U1. U1 is 400, which I'll write it as 4 into 10 to the power plus 2 is equal to M2. What is M2? 2 kilogram. So M2 is 2 into, what is V2? Root 2GH. So root of 2 into G is 10. And how much is H? It is given in the question that it vertical distance of 10 centimeters. So we have H is equal to 10 centimeter, which is 10 by 100 meter, right? Which is 10 to the power minus 1 meter. So this is into 10 to the power minus 1. So that makes into V2, right? This is this much, this term is V2 plus what is M1? M1 is 10 to the power minus 2 into next term is V1. Do we know V1? No, we need to find out V1. Okay. So now this becomes 10 to the power minus 2 into 10 to the power plus 2 becomes 4. This is equal to 4 into 2 into root of 10 to the power 10 into 1 into 10 to the power minus 1 is 1. So it is 10 to the power, so it is root 2, right? Root 2 plus 10 to the power minus 2 into V1. Okay, so this becomes 4 is equal to, what's the value of root 2? We'll take it at 1.4. So 1.4 into 2 is 2.8. So this is 4 is equal to 2.8 plus 10 to the power minus 2 V1. So 4 minus 2.8 is equal to 1 by 100 V1. 4 minus 2.8 is 1.2. So we have 1.2 into 100 is equal to V1, and therefore V1 is equal to 120, which makes the correct option as option C. See guys, I'm really sorry that I took so long. I mean, in fact, it takes almost every question that the explanation becomes really lengthy, and I'm trying my best to reduce the time. But see, these kind of questions, see, what I always suggest students is to understand the demand of the question, and the demand of the question here was to check whether you know the concept of ballistic pendulum. And not just ballistic pendulum, an extended application of ballistic pendulum. This, for this question here. So yes, so that is ballistic pendulum for you, and we say goodbye to the question. Let's be the next question, which says, okay, so one more question based on momentum, law of conservation of momentum. Okay, ball is striking with, okay. A rigid ball of mass m strikes a rigid wall at 60 degree and gets reflected without loss of speed. Mass m gets rigid wall, 60 degree, reflects, okay, without loss of speed, Vv. The value of impulse imparted by the wall on the ball will be, okay. See, to do this question, what we need to understand is the primary formula, which is impulse is equal to change in momentum, which is final momentum minus initial momentum. Since it is given in the vector form, we need to find out final vector minus initial vector. So I'll just explain the workflow. We'll find out the initial vector pi, we'll find out the final vector pf, and then we'll calculate the change in momentum vector. And then what we'll do, we'll find out the magnitude of the change in momentum vector. Okay, so how are we going to do this? Initial momentum, exactly, final momentum, change in momentum, and then magnitude of momentum. Okay, so what I'll do is we'll divide this into three parts: part 1, part 2, and this would be part 3. Okay, so let me draw the diagram first, and then we'll go to the part 1. So what do I mean by part 1? When I say part 1, I mean we are discussing only about this shaded region here, this much portion of the event that we are going to see. So we are going to discuss only the region where the ball is actually. So this will be part 1, right? This will be part 1 where the ball is actually hitting the wall. Okay. Now when the ball is hitting the wall, it is hitting with a velocity v at an angle 60 degree, right? So the given diagram actually represents a ball with mass m hitting the wall with velocity v at an angle 60 degree. Now what are we actually supposed to find out? We are actually supposed to find out the momentum vector, but what are we given? We've been given the velocity here. So what we need to understand is direction of momentum vector is actually the same as the direction of the velocity vector, which means if this represents the direction of velocity vector, we can safely assume that this over here represents the direction of momentum vector, which in this case would be initial vector pi. Okay, so that's the primary concept here. So if you've got that idea clear, let us now go into the finding out the initial momentum vector. So we need initial momentum vector. So what is initial momentum vector? It is a quantity which has both magnitude as well as a specific direction. So what is the magnitude of pi here? Magnitude of pi, we know that it is equal to mass into velocity because it is readily given in the question. Now what do we need to do? We need to find out the direction of this vector. And how are we gonna do that? Let us have a look at that. So okay, so to find that, what I'll do is I'll draw a diagram here. So let us say this represents the initial momentum vector AB. Okay, so AB is initial momentum vector. So this is magnitude of AB, which is equal to magnitude of initial momentum vector, which is equal to mass into velocity. Now see, what I'm going to do is I'm going to resolve this vector into two components. One, the vertical component, okay, and the other one, so let me call this as AC, the vertical component. Other CB is the horizontal component. So AC is the vertical component and CB is the horizontal component. Now let us try to give our maximum attention here. So how can we write vector AB as? So vector AB can be represented as a component, right? A component which is, let us write the component of AB along the x direction I cap plus component of AB along the y direction j cap. Okay, so this is what we have. Now, okay, I think the better way to write it can be written as AB, a component of AB in the x direction plus, okay, component of AB along the y direction. Now, why did I write it like that? I'll explain the reason behind that. See, if I were to choose a reference axis here, so say if this is our reference axis, okay, this is our reference axis. This is where the problem becomes really interesting and conceptual. So look at the direction of the head here. So the direction of AC vector, head is C. C is pointing downwards, right? Vertically downwards. Vertically downwards means it is acting like this. It doesn't mean that it acts like this. Vertically downwards simply means that the direction of motion is along the negative along the negative j direction or the negative y direction. Okay, so this is AC. So AC here is actually moving along. AC here is actually moving on the minus j cap, right? Similarly, what is CB? To find the direction of vector, we focus on the head. The head is B. B is an arrow. Arrow is pointing towards the right, horizontally towards the right. So this is where the vector CB is going. CB is actually moving towards the positive x direction. Therefore, it is along the positive I cap. So if I were to write vector AB, I would write like this. Vector AB is actually x component, which is CB, which is along the positive I cap, plus y component, which is the y component. Y component is AC. And where is AC along? AC is along the, so we have AC, and AC is along the minus j cap direction. I hope the concept is clear. Please go through the explanation once again. Go through it once again. Those who are watching online, please make sure that you pause the video, come back to this explanation more time. Things will become really clear to you. We have done that. And if things are clear to you, let us go to the next part, which is utilizing the given value here. What is given to us? See, it is given to us that this angle here is 60 degree, right? This angle here is 60 degree. So I can say here that this much angle is 60 degree. In which case, tell me what is sine 60 from the diagram. We can say that sine 60 from the diagram is equal to opposite by hypotenuse, which is, okay, let me explain that also. So if this is 60, opposite side is AC, hypotenuse is AB, right? In which case, what is AC? AC is nothing but AB sine 60, right? So AC can be written as AB sine 60. Similarly, tell me what is cos 60? So cos 60 from the figure is cos 60. This is 60. Cos 60 is adjacent by hypotenuse. Adjacent is CB, hypotenuse is AB. So we can write cos 60 as CB upon AB, and therefore CB can be written as AB cos 60. Now I'm going to erase out certain things to make the board look less cluttered. Okay, so this is CB is equal to AB cos 60, right? Now what I'll do is I'll bring these values. I'll bring these values over here. So I can write vector AB as, what is CB? CB from here is AB cos 60. AB cos 60 along positive I cap, plus what is AC? AC is AB sine 60. So that it would be AB sine 60 along minus j cap. Let me erase out these things as well. Okay, now let us see what is magnitude of vector AB. We've written here that magnitude of vector AB is nothing but mv. And what is vector AB? It is the initial momentum vector. So the initial momentum vector pi is equal to magnitude of vector AB, which is mv into cos 60 I cap, plus AB is again mv into, right, mv into sine 60 along minus j cap. Okay, so yes, this is what we're going to keep for the reference, and we'll bring this again in part 3. Okay, now having said that, let us move to part 2 of the problem. Now if you paid much attention to the part 1, I think part 2 will become really easy to you. But even though it's easy, I don't want to skip any step here. We'll go through the steps in detail. Okay, so the idea remains the same. We're discussing only the second part here, which is when the ball is reflecting away from the wall. And what is the idea? The idea is the velocity vector is at 60 degree, and if the velocity vector is 60 degree, we can safely say that the momentum vector final here is also at 60 degree with a magnitude of mv inclined at an angle 60 degree, right? Now in this case, let us call this as okay, so we use ABC, right? So let us use DE and F here. Okay, so if I were to say that this is the okay, so if I were to say that this is the final vector here, which is vector DE here, I know that vector DE will have both magnitude and direction. The magnitude is mv, but we don't know the direction. To find out the direction, what will we have to do? We will have to resolve this into two components. So we have one component along the direction here. So let us call this as the final vector PF. So this is final vector PF, the vertical component, and then another vector moves like this. So we have final vector along the x component, right? So this is what we have. Now, how do you write the final vector? So we can write that final momentum vector PF is equal to the one along the x direction plus the one along the y direction. Okay. Can we write it directly now? No. Why? Because we need a reference axis. So this is the reference axis of our choice. This is the reference axis of a choice. We have this as plus x. This would be minus x. This would be plus y, and this would be minus y. Again, let us use the term here. So this is df. So how do we find out df? Direction of df? Direction of df would be the direction of where the arrow is heading. So df is a vector, f is the head, f represents the head of the arrow, and the arrow is head of the arrow is representing towards downwards. So we can say that if this is vector d, vector df is acting along what we call as the minus j cap. Now, what is vector? Where is, okay, wait. Now we need to find out where this angle is, right? Oh, I almost skipped that part. Sorry, my bad. So if we were to represent the angle here, see if this, wait. See, if this angle is 60, we can say that this angle is over here is also 60. Why? Because of them being alternate interior angles. Okay, so the angle we are going to use here is this angle over here, 60 degree. Okay, right. Yeah. So now coming back to the explanation. So we have minus j, and f is the vector here, second vector. So if this is f, then fe is going towards the negative x direction. So just simple, fe, head of fe is e is pointing towards the negative x, and therefore fe would be in the minus I direction. Okay, so if we were to write down the final vector pf is equal to, it will be p of x along the x direction, which is ef along the minus I cap plus py is actually df, so it is df along the minus j cap, right? Okay, now what we'll do again, what we do is we bring out sine 60. What is sine 60? Sine 60 is opposite by hypotenuse. Opposite is df, hypotenuse is de. So I can write this as df upon de. So what is df from here? Df from here is de times sine 60. Similarly, what is cos 60? Cos 60 would be, this is 60, cos 60 is adjacent, which is ef. So it becomes ef upon hypotenuse, which is df, and therefore ef is equal to, wait, is there a mistake here? Oh, sorry, it's not df, right? It's d. Okay, so we have this ef into de into cos 60. And now let me erase out these things. Okay, now what we'll do is we'll write down the final momentum vector pf is equal to, instead of ef I can write de cos 60 along the minus I cap, plus instead of df I can write de sine 60 along the minus j cap direction. Let me erase these two. Okay, now we have done the calculation, and now we have both the initial vector and the final vector. Now all what is left is to subtract them. So give me a minute, let me just try to bring these concepts together. Part 1, sorry, oh my bad. So we have part 1 here, and this is part 2. So ball is hitting the wall, reflecting the wall. From this we found out the initial momentum vector, and from here we have the final momentum vector. And what is now we need to find out? What is delta p vector, which is the final momentum vector minus the initial momentum vector. What is the final momentum vector? So which is, what is pf vector? Pf is, Oh, okay, right. So we need to find out PF also. So PF is actually, what is DE? DE is MV cos 60 along minus I cap plus what is DE? DE is MV, so it is MV sine 60 along minus J cap. I'll write it over here. So it is MV cos 60 along minus I cap plus MV sine 60 along minus J cap minus the initial vector. Minus initial vector is MV cos 60 along the I cap direction plus MV sine 60 along the minus J cap direction. Okay, right. Now if we have both of these, let us open the brackets. So it becomes MV cos minus MV cos 60 I cap minus MV sine 60 J cap, minus into plus is minus, so this becomes minus MV cos 60 I cap minus into plus is minus, minus into this minus is plus, so this becomes plus MV sine 60 into J cap. If you observe it well, minus MV sine 60 plus MV sine 60 is 0. So all what we are left is minus MV cos 60 I cap plus this vector over here is minus MV cos 60 I cap. So this becomes minus 2MV cos 60 into I cap. Now this is where the vector notation becomes really important. So all of this is actually delta P. And what is delta P? Delta P is change in momentum, which is the impulse vector. So we have that the impulse vector I is equal to minus 2mv into what is cos 60? Sine 30 is equal to cos 60, which is equal to 1 by 2 into I cap. And therefore, the final momentum vector I cap is equal to, let me like this, will be equal to mv into negative I cap. And if you take magnitude on both sides, what you get? Magnitude of the impulse vector is equal to mv. Okay, option as option A, mv. A car is negotiating a curved road of radius r. The road is banked at angle theta. The coefficient of friction between the tires of the car and the road is µs. The maximum safe velocity on this road is. Okay, so what I'll do is I'll divide this explanation into two types. One, banking of road, okay, where the friction is not present, and then we'll discuss banking of roads with friction. So give me some time to draw a couple of diagrams, and then we'll discuss first banking of road without friction. Okay, so this is banking of road without friction. Now if there is no friction present here, if you draw the free body diagram, okay, let me first write down what are the given parameters here. So this angle is given to us as theta, and this, the radius is given to us as r. So we know that the forces acting on this car would be, the weight acting downwards and the normal reaction along being resolved in n sine theta and n cos theta, right? So these are the various forces acting on it. Now let us see the condition. Now what will be the condition here? We know that there is no net motion along the y direction, which means sigma Fy will be equal to 0. And according to Newton's second law of motion in circular motion, we can say that sigma Fx should be equal to the F centripetal, right? So let us first look at these two resolutions and then we'll write down the equations. Okay, now if sigma Fy is equal to 0, let us resolve the normal force into n cos theta and n sin theta. Okay, so I have not taken that diagram here, so to bring much clarity here. So we have n cos theta and mg along the y direction, right? So if you were to write the equation here, how will you write the equation? We can write that n sin theta, sorry, we can write that, okay, wait, we have not written it here. Okay, so we can write here that n cos theta minus mg is equal to 0. Therefore, we can say that n cos theta is equal to mg, right? This is what we get for sigma Fy is equal to 0. Now, wait, sigma fx is not equal to 0. Why? Because sigma fx is actually the centripetal force. Sigma fx is actually, right? So sigma fx is the, wait, what's, yeah, so sigma fx is the centripetal force. Now, what is the only force acting along the x direction? It is the x component of the horizontal component of the normal reaction, which is n sine theta. And what we have, the other force is F centripetal. So when we say sigma Fx is equal to F centripetal, there's only one force. And since it is acting along the net direction of motion, we can say that n sine theta, which is this component, is equal to F centripetal. And therefore, n sine theta is equal to F centripetal, which is mv squared by r. Let us take this time as capital R, right? mv squared by r. Okay. Now let us bring these two equations, which is n sine theta is equal to mv square by r, the whole divided by n cos theta is equal to mg, and then we will divide these two equations. So what do we get? N by n is m1, sine theta by cos theta is tan theta, m by m is 1, and therefore what we left is v square by rg. And therefore, what is v square? V square is equal to tan theta rg. And therefore, what is v? V is therefore equal to root of rg tan theta. Okay. So that's the maximum velocity. That's the maximum velocity. That's the maximum velocity which the car will turn on a banked road. On a banked road. But what is the condition? Banked road without friction. Banked road without friction. Okay. Now let us see what happens in the case where there is friction. So when we discuss banking of road with friction, what are the various forces acting on it? Mg will act downwards. Then we have the normal reaction which is acting perpendicular to the surface, which can be resolved into two components, n cos theta and n sin theta. And then we have the frictional force which is acting downwards along the slope of the block or the banking, right? Now in this condition, let us apply sigma fy is equal to what it is? It is m into ay. Is there any motion along the vertical direction? No, there is no motion along the vertical direction, which means acceleration along vertical direction is 0. This means sigma fy is equal to 0. And what is sigma fx? Sigma fx is nothing but m into ax, which can be written as F centripetal again. So let us now try to draw the free body diagram in a detailed way to find out sigma fy and fx. And this time I'll draw it more. I'll increase the number of diagrams so that the concept becomes more resolved. Okay. Right. So now, see, let us first resolve friction. So this is the way friction is been acting in the along the slope, right? So if this angle is theta, right? If this angle here, see if this angle is theta, which means I'm marking this angle over here, right? So this angle theta represents this angle theta. And if I were to resolve friction like this force here, can I draw a horizontal line here and then say that these two lines, okay, let me name these two lines. So maybe AB is parallel to CD, and therefore angle ABC and angle BCD are alternate interior angles, and therefore these two angles are equal, right? In which case I can use this triangle to resolve normal reaction, and these are two coincident vectors now. So I'll travel from going from B to C. I'll go from B to A first, and then from A to C, and therefore I have the resolved components of FR. And how will I write it? I will write them like this. So this would be, see, this angle is theta, right? So this component is cos theta. So I can write here n cos theta. Now this component over is the opposite component, which is sine theta, and therefore I can write this component as n sine theta, right? Which means, I'm sorry, this is not normal reaction, right? This is friction. So I can write this as Fk cos theta, and similarly I can write this as Fk sine theta. Now the same concept when we discuss about the resolution of normal reaction. So we can say say for example, draw perpendicular here, right? If this angle is theta, now see we've been repeatedly telling the same derivation many of times, so let us not go through the same derivation again. So I can resolve this angle by vertically opposite angle. This will also be equal to theta, right? So if this is theta, vertically opposite angle, this angle is also theta. Now if we resolve this normal reaction, how can we write this as? We can write the normal reaction as, say, so this is the adjacent side, so this will become n, this will become n cos theta, and this is the opposite side, so this will become n. Okay, fine. If you want, let me draw that one more time. See, this is the normal reaction here. Normal is acting like this, right? So can be resolved into two components, one the vertical component like this, and other the horizontal component like this, where this is theta. So this component is the opposite component, so that will become n sine theta. This is the adjacent component, and therefore that will become n cos theta. Simple. Okay, now having said that, let us see the condition. Sigma Fy is equal to 0. Now why is sigma Fy is equal to 0? Because there is no net movement in the y direction, therefore acceleration along the y direction is equal to 0, and therefore sigma Fy will be equal to 0. And now if sigma Fy will be equal to 0, let us see what are the various forces acting in the y direction. There is one component of Fk acting in the y direction, which is Fk sine theta. So let it over here. We have Fk sine theta, and there is one component of normal reaction acting in the upward direction, which I'll write it here as n cos theta. So therefore from this condition we can write that if sigma Fy is equal to 0, we can write that n cos theta is equal to Fk sine theta. Now what is Fk sine theta? What is Fk? We can therefore write that this is n cos theta is equal to, see what is Fk? Fk is nothing but mu k into n into mu k into n into sine theta, right? So this is the condition with y direction. Now let us see what happens when we come to x direction. Okay, so one more time we will try to see the concept of resolution in detail. So what we have here is the plane road, the banked road, friction is acting downwards. Normal reaction component cos theta sine theta, which means normal reaction is acting like this, right? So we have normal reaction acting like this, okay, right? And when we discuss about the horizontal forces along the x direction, we therefore need the F centripetal, because by Newton's applying Newton's second law in circular motion, we can say that sum of forces in the radial direction is actually equal to the centripetal force. So this is a centripetal force acting into the center of the road, right? Acting into the center of the road, where n sine theta acts along it. Now we need to resolve the frictional force into horizontal and vertical. So as we did in the previous section, this is parallel line. These two are parallel lines. So let me write them one more time. So we have AB is parallel to CD, and therefore if you assume this FK as the side of triangle BC, then we can have triangle ABC, right? We can have triangle ABC. Okay, that's been already explained, so let's not waste time here. So we can write this part as FK sine theta, and we can write this part as FK cos theta. And normal reaction, we have already resolved it. What we have is this part as n cos theta and this part as n sine theta. Now see what are there are two forces. One is Fr and the other is normal reaction. What is the x component of normal reaction? It is n sine theta, right? So n sine theta acting towards the left is one component, and for the frictional force we have one more component which acts towards the left, which is the Fk cos theta. Fk cos theta is acting towards the left, and therefore we can write here as Fk cos theta. And if sigma Fx is equal to F centripetal, then what can we say? See, since both of these two forces and the net direction of motion is actually along the same direction, right? Along the same direction. Therefore we can write that. Fk cos theta plus n sine theta is equal to mv square by r. Now what is Fk? Fk is nothing but mu into n. So we have mu into n cos theta plus n sine theta is equal to mv square by r. Okay. Now let us bring these two equations together and then try to solve the unknown variable, which is v here. Okay, so n sine theta plus fk cos theta is mv square by r. We got it from solving the forces along the x direction. For y direction, we have n cos theta is equal to mg plus fk sine theta, and we know what is the value of fk. It is mu k into n, right? What's the value of fk? It is mu k into n. Now, how do we solve this equation? So for that, what I'll do is I'll rewrite this equation as n cos theta minus mu k into n sine theta is equal to mg. Which equation? This equation over here, right? And then I'll bring this equation over here. Then what we do? Then what we do is we divide these two equations. So let us see what do we get while dividing them. So when we divide them, what we get is n cos theta minus mu k into n sine theta, the whole divided by, now see, I'm going to do a small algebraic manipulation here, the whole divided by n sine theta plus mu k into n plus mu k into n cos theta. Okay. Now the LHS remains the same, which is m into g divided by mv square by r. And here what I'll do is I'll divide this entire equation by n cos theta. So I'll divide this entire equation by n cos theta. Okay, so I'll divide this equation by n cos theta, this equation by n cos theta, this equation by n cos theta, and this equation also by n cos theta. Now let us try to understand what happens. So n cos theta by n cos theta is 1, so this becomes 1 minus n by n is 1, sin theta by cos theta is tan theta. Everything remains the same, 1 minus mu k into tan theta, the whole upon n by n is 1, sin theta by cos theta is tan theta, plus n by n is 1, cos theta by cos theta is 1, so all we get is tan theta plus mu k is equal to mg into, okay, now wait, now we have m by m is 1, so all what we have is g by, sorry, is v square by r, so that becomes gr by v square. In which case, what is v square is equal to? V square will then be equal to tan theta plus mu k, the whole divided by 1 minus mu k times tan theta into rg, right? And therefore, what will v become? V will therefore become root of tan theta plus mu k into rg, the whole upon 1 minus mu k tan theta, which brings us back to the question, which gives us the answer to tan theta into rg. So rg mu s plus tan theta by 1 minus, okay, so this gives the correct option as option A. Okay, that was a lengthy solution because see, it becomes time consuming when we try to elaborate each and every step. So, which in this case was resolution of forces, which is the key point in understanding the understanding the question here. Without which it becomes really difficult. Now, those people who have attended the class, otherwise they know directly that the formula is rg into mu plus tan theta. We have been discussing this many times in the class, but others who have missed the class and those who are watching online, please make sure that you try to understand the derivation, derive it a couple of times on your own, and then things will become more clear to you. Okay, typically not a NEET level question, I have to say that. Typically not a NEET question. It was a bit time consuming. Even if you were to do it in the exam hall, or simulation, it will take at least 2 to 3 minutes when you're doing it for the first time. Okay, let's now move on to the next question. A uniform circular disc of radius 50 cm at rest is free to turn about an axis which is perpendicular to its plane and passes through its center. it is subjected to a torque which produces a constant angular acceleration of 2 radians per second. Its net acceleration in meter per second, its net acceleration in meter per second square at the end of 2 seconds is approximately. Okay, so first let's me draw a diagram and then we'll go into the details of this. Okay, so a uniform circular disc. So this represents a circular disc of radius 50 centimeter. Radius is 50 centimeter at rest. So at t is equal to 0, we can write that omega 0 is equal to 0. Okay, is free to turn about an axis which is perpendicular. So if we were to assume a plane that is perpendicular to this, so this might be the plane, right? The plane containing the disc. So yes, so we have the plane containing disc. There's a disc and it is perpendicular passing through the. Okay, now we have to mark the center. So it is passing to the center. Okay. It is subject to a torque. So this is the external torque acting on it. Okay. So let us say this is torque external. Why not F external? Because we're not talking about linear motion. We're talking about circular motion where force is analogous to torque, right? Okay, so torque external. Now, when it is rotated like this, what happens? There will be displacement in the disk, and this point A will say it after 2 seconds, it moves like this and gradually reaches here. So if we have to mark the displacement, it will look something like this. So there's this much amount of. My bad, if there is this much amount of displacement, okay, and the body and the position A is reached now. Okay, now constant angular acceleration. So we can say that during this motion, angular acceleration alpha is given to us as 2 radians per second. Okay, 2 radians per second. Now we need to find out the net acceleration. Okay, so the logic, the first thing we need to understand is what is net acceleration. Let us first understand that point. So say at this point A, there are 2 components of acceleration. One, which is the tangential acceleration AT, and the other, which is the centripetal acceleration AC. Now this will remain the same when the object is in motion. So say at this point it is tangential acceleration AT, right? And then we have centripetal acceleration which is acting towards the center. Okay, so one more time we have, so at this point A we have one component of acceleration which is centripetal acceleration AC, and we have another component of acceleration which is tangential acceleration AT. And what is tangential acceleration formula AT? Tangential acceleration AT is given by r times alpha, and what is centripetal acceleration AC? It is given by r. So it is given by r omega square. Okay. So now let us find out these 2 values. So what is okay? It's getting a bit clump stuff here. Okay. So what is AT? AT we just wrote it as r into alpha. What is the value of r? Given to us as 50 centimeters. So this becomes 50 upon 100, right, into alpha. What is the value of alpha? 2 radians per second. So this is 2. So it is 10 by 10, which is equal to 1. So tangential acceleration AT is equal to 1. Now what we have is AC. So what is AC? AC is r into omega square. Now how do we write r into omega square? What is r? R is again 50 by 100. And what is omega square? See, omega is actually omega 0 plus alpha into t, right? Now what is omega 0? Omega 0 is 0, and therefore omega 0 becomes 0, and what we get is omega is alpha into t. Therefore what is omega square? Omega square is alpha square t square. So instead of omega square, I can write here alpha square into t square. Therefore AC becomes 50 by 100 is 5 by 10 times what is alpha? Alpha, the value of alpha is given to us as 2. So this becomes 2 square into t. T is also 2 seconds. So into 4. So 2 square is 4. 4 square, 2 square is 4. 4 is 16. 16 into 5 is 80. 80 by 10 is 8. So what we get is AC is equal to 8. Now if AT is equal to, sorry, so we can write here that AC is actually equal to 8, and we can write that AT, right, AT is equal to 1, in which case what is A net? A net is equal to root of AT square plus AC square, which is equal to root of, what is AT? AT is 1 square plus AC is 8 square. So what we get is root of 65. So 7 square is 49, 8 square is 64. Therefore, the value should be definitely greater than 8, and therefore we round it to be 8, which gives us the correct option as option D. A spring of force constant K is cut into the lengths of ratio 1:2:3. They are connected in series and the new force constant is K prime. If they are connected in parallel, the new force constant is K double prime, then K prime is to K double prime is in the ratio. Okay. See, so this question is basically asking or is evaluating your knowledge of combination of springs. Okay, which of course is in series and in parallel. So first we'll have a understanding about this topic, combination of springs in series and parallel. Then we'll get to a conclusion what to exactly apply in this question. Okay, so give me a minute. I'll write down the basic concept of combination spring. Then we'll see how to do this. So to understand the concept of spring okay, let us not discuss spring in series first. Let us discuss springs in general. So I've taken the example of two springs here, spring 1 and spring 2. Now, the earlier condition of the spring, say it would be like this. So this is spring 1. Okay, this is spring 1. And now there is no mass attached here. When there is mass attached here, so what happens is, when there is mass attached here, what happens is the spring will undergo elongation, and this length spring, it undergoes elongation. Now let me mark this as the terminal point of the spring as reference here. Okay, so this is the terminal point of the spring. It was earlier like this. In the final condition, the terminal point got displaced by distance x1. So when mass m1 is tied, displacement is x1. Similarly, for spring 2, what we say is, say this was the condition earlier. Okay, this was the condition earlier. There was no mass attached. So there was no mass attached, and now what's happening is that we have hooked the mass into this end of the spring, and therefore this spring will also undergo some elongation, and this is the terminal point. And what we see is that the distance between the initial position of the terminal point and that of the final position is x2. Therefore the elongation is x2 when the spring 2 is attached with a mass m2. Okay, now we know by Hooke's law that F1 is actually equal to minus K1 x1. Why F1 is minus K1 x1? Because negative implies that the force is restoring in nature, right? Similarly, we have F2 here is equal to minus K2 times x2. Okay, so I hope this much is clear. Okay, in the graph, what I've done is I have taken F on the y-axis and x on the x-axis, and we know that since this equation is of the form y is equal to mx, it simply means that we have y on the x-axis, f on the x-axis, x1 on the x-axis, and therefore we have the slope being k. So which further implies here that this slope is actually k1, right, and the slope here is actually k2. Now from this graph, it is very clear that slope k2 is actually greater than slope k1, right? Now if slope k2 is greater than k1, what does it mean? What does it imply? That is the fundamental concept behind this question. See, when we say that a spring with spring constant k2 is greater than a spring with spring constant, so what is k? K is the, my bad, I forgot to write it over here. So k is the spring constant. So when we say that spring constant k2 is greater than spring constant k1, it simply implies that spring with the spring constant k2 is a what is a more exactly is a more stiffer spring, right? Is a more stiffer spring. And what is the spring with spring constant K1? It is a less stiffer less stiffer spring. So all of this based on the elongation that has took place by attaching the respective bodies. Okay, right. Okay, now, oh well, if this explanation has to make more sense, this has to be M1. This has to be M1. Why? Because only the same weight attached together, we can compare these two springs. Okay, so that's it with the basic logic of spring constant. Okay, now let's see what happens when springs are connected in series and in parallel. Now we'll discuss combination of springs. How? We'll again use the same example of two springs. Okay, so now we have spring 1 with spring constant. Okay, let me write that also. We have spring number 1 with spring constant K1. When the spring is loose, it remains unextended. When the mass is attached, the spring will undergo extension, right? The spring will undergo extension. Similarly, when we have spring 2 with spring constant K2, it is unextended. When it is attached to a mass M, it will undergo extension, right? This is something we know. Springs being attached to a common wall. So this is the wall. These two springs were individually hanged. Now we have spring 1. So basically what happens is this spring is actually detached from here, right? If you see, this spring is detached from here and it is then hooked onto this. So basically, how do you get this diagram? You just hook the spring over here. This is how you get the new diagram, which is diagram number 3. So we have the spring constant attached to one wall. There are two ends of it which is free, and in the next end what happens is the spring constant with spring constant K2, sorry, the spring with spring constant K2 is attached, and to this combination we are going to put a mass here. Okay, attach a mass here. Now when we attach that mass, what happens is that mass will cause the elongation of both K1 and K2, and therefore what will happen is the mass will cause elongation, and the terminal point of the spring, these two springs will come down like this. Okay, so this was the earlier position of the terminal point. This is the terminal point in the final position now, and as we know directly from the figure that this total displacement here will actually be equal to the sum of the displacement of these two. Why is it so? It is so because the force, the net force acting on this series combination will actually be the same acting on both F1 and F2. Not clear? Will be more clear. It means that the net force acting on the combination of series is the same force which otherwise would act on both these springs equally. Okay, so F spring 1 and spring 2, both of them will face both of them will experience the same amount of force. Now what is F1? F1 we know that is is minus K1 x1, and what is F2? It is minus K2 x2. So what is F is equal to F1 is equal to F2 x2? It can be what is F1 is equal to F2? It can be replaced by one single term F. But what's important to understand here is that the total displacement, new displacement here will be actually equal to the algebraic sum of x1 and x2. So now this is where things become, beautiful when it comes to the analysis. Why? I'll tell you. From this equation, what is x1 is equal to? X1 is actually equal to, right? X1 is equal to x1 is equal to F1 upon minus K1. What is x2 is equal to? X2 is equal to F2 upon minus K2. Now if I were to substitute these two in this equation here, what do I get? X is equal to x1, which is F by minus K1 plus what is x2 is equal to? X2 is again, this should be F1, right? This should be F1 and F2. Okay, so we have got here F1 and F2 by minus K2. Now what is x? X otherwise is for this new spring. So this is the new spring, right? This is the new spring which has a spring constant of x, and the total force acting here is F, right? And the new spring constant is K, which is K series. So I can write here that F is equal to K series into X. So instead of X, I can write here F upon K series, of course, minus, right? Now, what is the beauty here? The beauty here is that F is equal to F1 is equal to F2. Therefore, I can write this equation one more time as F by minus K series is equal to F by minus K1 plus F by minus K2. And if you were to cancel F and minus and minus and minus, what do we get? What we get is 1 by K series is equal to 1 by K1 plus 1 by K2. Or this otherwise is equal to K2 plus K1 upon K1 K2 is the concept here, right? Now, what did I say earlier about a stiffer spring and a softer spring? So that's what we are trying to come here. Okay, so see, if you have a spring constant K1 and a spring with spring constant K1 and another with spring constant K2, if you put them in series, what you get is a new spring. What you get is a new spring. Essentially, what you get is a new spring with a spring constant K series, which is actually equal to the reciprocal of this, right? Yeah, will be equal to K1 into K2 the whole upon K1 plus K2. Therefore, what is the significance of this? Let's try to understand this graphically. If you have to understand one step further, say for example, if K1 is equal to K2, right? If K1 is equal to K2, now what is K series? Now K series is actually equal to K into K the whole upon K plus K, which is equal to K square upon 2K, or which is equal to K by 2. What does it mean? It means that if we have a spring with spring constant 1, now this being equal to K1, and if we have another spring which with the same spring constant, okay, same spring constant being K2, such that K1 is equal to K2. Oh, okay, let us leave that. Okay, let us say, okay, since that we have written this point, let us consider that. It means that when these two springs are connected in series, we get a new spring. We get a new spring which K series such that K series is less than, okay, K series is equal to K1 into K2 the whole upon K1 plus K2. And therefore, when springs are connected in series, what do we get? We get a softer spring. Is the concept here. Yes, I do understand that the derivation is a bit messy. I would suggest you try to take it down on your own, try to draw these diagrams on your own and this graph also, then things will become more clear. Or what you can do is you can stay patient, follow the derivation for the same derivation for springs in parallel, things will become crystal clear to you. Give me 5 more minutes. So now we have the diagrammatic setup for combination of springs in parallel. So what happens here is we have a wall spring with spring constant K1, another wall spring constant K2, both of them have the same mass. Now when we say that these two springs are arranged in parallel, what we essentially do is both of them are connected together with one rod and the mass is distributed by this rod equally to both these springs. Okay, so same wall, same mass through a common rod. Okay, so when I say rod, this is the rod that I mean. This is the rod. Okay, right. So what essentially happens, if you just try to understand the vector point of view, what happens here is there's one rod here, right? And this is spring 1. This is spring 1, which will actually exert a force F1 in the opposite direction. There's another spring 2 here, which will exert a force F2 in the opposite direction. And the net force will be experienced on the mass M, F. And by vector approach, what can we say? We can say that F is actually equal to F1 plus F2. This is the logic here. Okay. What also is interesting is that this mass M, when this is placed on this rod, when it undergoes elongation, what we need to understand is that elongation experienced by the spring 1 will exactly be the same as elongation experienced by the spring 2. Now, most of the time students try to have complicated ideas here. This condition applies only for ideal situations, which means there might be cases where this is spring 1 with this elongation, okay, and this might be spring 2, this might be spring 2, okay, wait, give me a second. So this can also be a case where the mass is attached like this, where the mass actually settles like this. So there are practical conditions wherein these situations don't work, so we're not talking about those. In those cases the mass distribution varies, the non-ideal forces comes into picture, which is not something that we do here. That's completely for an engineering domain to discuss. We are here already discussing about the ideal things. So when we discuss about the ideal things, what remains constant? The spring constant, even though is not constant, the displacement caused due to this spring is constant for both the springs. So the spring 1 and spring 2, both of them will have only the same elongation. Therefore, we can say that x is equal to x1 is equal to x2. Now, what is x? X is the new spring which has the force in parallel, which has the spring constant k in parallel, which has the displacement x. Okay, now we know that displacement x is equal to x1 is equal to x2, and what gets divided here? The total force gets divided in F1 plus F2. Now, if you write this further, what is F1 is equal to minus K1 x1? What is F2 is equal to minus K2 x2? Similarly, what would be F parallel is equal to? F parallel would be equal to minus K parallel into x, right? So if you were to bring all these values here, what is F parallel? F parallel is minus K parallel into x, which is equal to, right? Which is equal to, what is F1? F1 is minus K1 x1. So we have minus K1 x1 plus, what is F2? F2 is minus K2 x2. Now, what is common here? What is equal to all these three springs? X is equal to x1 is equal to x2. Therefore, we can replace this as minus Kp is equal to x is equal to minus K into x1 plus minus K2. Instead of minus K2, we can write, sorry, instead of, oh, wait, what did I write? My bad. So now we can write here that, so this same equation, now what can we do? We can bring x is equal to x1 is equal to x2. So instead of x1, right? Instead of x1, what can I write here? Instead of x1, I can write this as x. Instead of x2, what can I write here? I can write this as x. And now what will get cancelled? X will get cancelled. Negative sign will cancel. So what we get is Kp, which is parallel, springs in parallel, is equal to K1 plus K2. Right? So we get Kp is equal to K1 plus K2. What is the graphical interpretation again? If we have two springs with spring constant K1, or let's say if K1 is equal to K2, then what is Kp? Kp is actually 2 times K, right? Because K1 plus K becomes K plus K. It's 2 times K, which means when you arrange two springs in parallel, the net spring constant is increased. So if this is spring 1, right? If this is spring 1, and say this is another spring, which is spring 2, and if you then put 1 plus 2 in parallel, then what you get is actually a new spring. What you get is a new spring. And is the spring softer? No. This spring is a more stiffer spring, right? This is a more stiffer spring. This is the concept that you should understand from the conceptual point of view. Now let me just see. Now writing all of this is becoming really difficult. I totally understand that. So what I'll tell you is, if you want, you can carry out this discussion, this explanation. For those students who are listening to this in online mode, please make sure that you write this derivation one time on your own. Things will become even more clear to you. Now, for those who just want the gist of it, I'll just put these things into a table. Give me a minute. I'll write on the table, and you can carry over that table whenever problems are asked from this topic. Okay. So this is the table. What do we have here? Combination of springs. In which conditions? We have combination of spring in series and combination of spring in parallel. So the first characteristic, displacement. What is x? X is the elongation. What is F? F is the spring force, right? F is the spring force. What is X? K? K is the spring. K is the spring constant. So we know whenever we connect two springs in series and in parallel, we eventually get a new spring. Whenever we connect two springs in parallel, we eventually get a new spring. This new spring will have new constant, which will be x parallel, new force F parallel, right? And new spring constant, which is K parallel. When we connect springs in series, we will have new displacement X series, new spring force Fs, and new spring constant Ks. Now, what will be the Xs? Will be equal to the algebraic sum of individual displacement. So, what is the concept here? How do we study this? In series, the force remains constant. In parallel, the elongation remains constant. In series, the elongation gets added. In parallel, the net force gets added. Okay. In series, the net along the springs constant will be k1 k2 by k1 plus k2, whereas in parallel it will be k1 plus k2. So the net result is, when you connect this thing in connect the springs in series, the new spring is actually a lighter spring, whereas when you connect this thing in parallel, what you get is a more stiffer spring, right? Now, using these two, let us come back to the question and try to solve this. I hope you, if you have given much emphasis on the way of note taking, and if you have discussed this among yourself, you will have a clear understanding about the question, the concept of series and parallel. Now, those who are watching it online, please, this is a request, you try to watch it a couple of times. Try to write down note a couple of times and then come to this part of the solution. Things will become more clear to you. Things will become permanent in your mind. So let us see. Now, in this question, what's given is, there is a spring with length L and spring constant K, which is divided into 3 springs in the ratio such that the length is 1, 2, 3. And then these 3 individual springs are connected in series as well as they are connected in parallel. Now, how do we approach this? We have been asked to find out the relationship between Ks and Kp. Okay, so we'll try to see this. See, what is Hooke's law? From Hooke's law, we have F is equal to minus Kx, right? Now, connected in series and the force constant is K dash. They are connected in series and the force constant is K. Okay, so what we need to understand is, if force is a constant here, okay, if force is a constant here, we can say that K is proportional to, now I'm ignoring the negative sign here, K is proportional to 1 by X. Of course, that makes sense, because it means that if K is more, then also if X is less, then K is more, which means if X is less, this elongation is less, then we have a more stiffer spring. And if X is more, it implies that the spring is less stiffer in nature. This is the concept, right? Okay. Now let us assume the original length of the spring to be 1x plus 2x plus 3x, 6x. And when it is divided in the ratio 1:2:3, we get the springs as of springs with lengths as 1x, 2x, and 3x. Okay, right. With this, let us see how to approach this question. So we know that k is proportional to 1 by x, which means k into x is a constant, which means k into s is a constant, and this will be constant for all the 4 springs. So if I were to write this, how can we write? We can write the spring with this equation as capital K, that is a spring constant. So say, okay, what letters do we use here for ease of clarity? Okay, let us use it. So we have spring K into, instead of x, we'll have 6x, right? Here it will be K1 into, right? K1 into, okay, or maybe to understand to make this concept better, I can write like this: K into capital L, K into L1, K1 into L1. For this spring, we'll have K2 into L2, and for the third spring, we'll have K3 into L3. Now we know that K into L will be equal to K1 L1. K into L would be equal to K2 L2. Similarly, K into L will also has to be equal to K3 into L3. Right? Why? Because K into X is a constant. Now, for the same force applied. Now this equation, we can write this one more time. But this time, what will L1 be? L1 would be 1x. And what would be L? So let me erase. Okay. So we have K here, and instead of L, we have 6x. This would be K1, and instead of L1, what do we have? L1 is 1x. So into 1x. So we have 6kx is equal to K1 into x. And therefore, what is K1? K1 is actually equal to 6k. Right? Doubt? We'll clear it one more time. So what is L? L is 6x is equal to K2 into, what is L2? L2 here is 2x. So I'll write here into 2x. Now if you combine this, what do you get? 6kx is equal to 2 into K2x. So x by x is 1, 6 by 2 is 3. So what we get is 3k is equal to K2. Similarly, in K3, what do we get? K into, what is L? L is 6x. 6x is equal to, what is K3? K3 will be written as K3. But what is L3? See, from L3 here is 3x. L3 here is 3x. So we can write here 3x. What do we get here? 6kx is equal to 3 into K3x. And therefore, 2k, x by x is 1. So 2k is equal to K3. Now all what we need is these values, which is K1 is equal to, this is K1, right? Yeah, K1 is equal to 6k, K2 is equal to 3k, and we have K3 is equal to 2k. And what is the equation? What is K parallel? It is 6k plus 3k plus 2k, which is equal to 11k. And what is K series is equal to? K series will be equal to, okay, let us not make any confusion. So we have 1 by K series is equal to 1 by K1, which is 1 by 6k plus 1 by 3k plus 1 by 2k, which will give you 11k upon, which will give you 6k, right? So this will be 6 by 1 plus 2k plus 3k. So this will give you 6k upon 6k, which is equal to 1, which means the spring is, it's as equal to saying that this is the original spring. So it is to find k prime is to k double prime. What is k prime? It is series. So k series is to k parallel will be equal to 1 is to 11. And therefore the correct option is option C, 1 is to 11. I think there is a mistake, right, in the LCM. Yeah. So what is that? That should be, we don't need k here, right? Yeah, we don't need k here. What you get is 1 by 6k. And now what we get is simple. We're going to 1 by k. So now these two k will eliminate. Yeah, now it's correct. So what we get is 1 is to 11. So that's the answer for you. A really good question, which actually, see, I would have directly solved this question at this step. How? Just by taking K1 L1, K2 L2, K3 L3, and KNL. But the reason why I explained so much is that I want you to understand the way, how did these formulas arrive? How did we come to K parallel and K series? Because that is the concept. Okay. Right. Having said that, let's move to the next question, which is connected to a particle of mass m, and the other end is connected to a small peg on a smooth horizontal table. If the particle moves in a circle with speed v, the net force on the particle will be, okay. So the options are actually T plus mv square by L and B T plus and C is T minus mv square by L. So smooth horizontal table, net force along the center, circular motion. Okay, right. So as usual, we'll do it in three parts. First, we'll visualize the concept. Second, we'll see the free body diagram. And third, we'll apply the Newton's second law of motion. If we were to visualize this, this is what we have here. We have a table, right? And this is the peg, the wooden peg or any peg. Now this here represents the string and this is the ball or the bob, whatever it is, or particle anything. Now what is this bob doing? This bob is exhibiting circular motion within the table. This bob is exhibiting circular motion like this within the plane of the table. So if you were to see the top view, this would look like table, the surface of the table, right? This actually represents the surface of the table. This is the peg, thread, and now we have the bob executing circular motion like this, or the particle executing circular motion. Now let us see the various forces acting on this bob. So if we are to analyze the various forces acting on it, we know that the first primary force acting would be mg, and then we have reaction on the bob or on the particle due to the surface, right? Okay. So that is the force acting in the vertical direction. And which force is acting along the horizontal direction? See, since the string has a point of contact here, we know that tension is always away from the point of contact, and therefore the tension direction is towards the center. Now, see, this is the circular motion actually traced by it, right? Circular motion. This is how the object is tracing the circular motion, and this is the center of it. Now, when we say center, we definitely have radius, right? We definitely have radius. And when we say radius, since this is the string, we can say that length of the string, let me write it down here. Length of the string is actually equal to the radius of the circular motion, right? Radius of the circular path. Radius of the circular path. Therefore, we can say that R is actually equal to L here, right? So instead of R, we can write here length of the string, which is, according to the given equation, L. Okay, right. Now we also know that when the object is in a circular motion, there is an acceleration which is mv squared by r. Now what is centripetal acceleration? See, this is the concept which I would say the question is trying to test on you. Centripetal acceleration means that acceleration that is pointing towards the center. Centripetal towards the center. So what is centripetal force? Centripetal force is that force that is pointing towards the center of the circular motion. Okay, I repeat. So what is centripetal acceleration? Acceleration that is pointing towards the center. What is centripetal force? Any force that is pointing towards the center. Now let us see the various. Okay. We see in the various forces. Now let us see how to apply them. Newton's second law of motion. So we'll apply Newton's second law of motion both in vertical and in horizontal direction. So we know that sigma Fy is equal to may and sigma Fx is equal to max. Since there is no vertical motion in the since there is no motion in the vertical direction, we can say that net vertical motion is equal to 0, and therefore Ay should be equal to 0. And if Ay is equal to 0, then we have sigma Fy is equal to m into Ay is equal to m into 0 is equal to 0. And what are the various forces acting in the vertical direction? We have N and mg, and therefore we can write here that N is equal to mg. But then this has nothing to do with the question given. Why? Because we have been asked to find out the we have to find out the force that is acting along the center. These two are definitely not acting along the center. Now, if we had read sigma Fx is equal to m into ax, right? Sigma Fx is equal to m into ax. So we can write a sigma Fx is equal to m into, instead of ax, what do we have here? Instead of ax, what we have is the centripetal acceleration. So we have m into ac. So instead of ac, we have instead of centripetal acceleration along x component, we have AC. Now, what is the value of AC? See, AC we know is mv square upon r. What is mv square by r here? We just said that r is basically equal to L because length of the string is basically the radius of the circular path. Therefore, we have mv square by r will now be replaced by mv square by L. Now, let us see the sigma Fx part. See, which forces are acting along the x direction? So maybe we can draw one more. Maybe we can draw one more free body diagram here. So this is the bob, right? This is normal reaction. This is mg acting, and we only have one force that is acting towards the left, which is tension, right? Is there any other force? No. Which simply means that the only force acting along the x direction is tension. Sigma fx is actually tension alone. So tension is equal to mv square by L. What does it mean? See, it means that it actually means that mv square by L, or let me put like this. Let me retake this equation one more time. See, if sigma fx is equal to m into AC, right? If sigma fx is equal to m into AC, what I should do is I should write sigma fx as sigma fac. Oh, sorry, sigma fc. Now, what is sigma fc? Sigma fc is actually the what we call as the centripetal force, because centripetal force will be mass into centripetal acceleration. Very simple, right? So what if you just try to connect these two? What does it mean? It means that the centripetal force is actually the tension in the string. So if we were to write it otherwise, there is no special force what we call as the centripetal force, right? So here tension acts as the centripetal force. Students often ask me which force is centripetal force. How do we mark centripetal force? How do we mark centrifugal force? See, centripetal force is not a force on its own. Centripetal force is any force. I repeat, centripetal force is any force that is acting along the center of the circle where which the circular motion is taking place, and it is this force which causes the circular motion as such. I'll give you a couple of examples extending this question, and then things will become very clear to you. So if you were to see this, this satellite here is in circular motion. Why? Because it is actually exhibiting a, so give me a minute. So if you see this, this is the direction of the circular motion. The satellite is moving around the Earth, and at this point, if you try to understand this, the satellite is in a circular motion because there is definitely a centripetal force acting here, right? Yes. The electron is spinning around the nucleus because definitely it is exhibiting a circular motion. Therefore, there has to be a F centripetal. When a car is moving in a circular path, so if you were to, if you just complete this, so if you consider this as a road, it simply means that it is a circular road here, right? It's part of a circular road, and therefore when the car reaches this position, definitely yes, there is some centripetal force which is acting towards the center. Now all of these are F centripetal. But what is this centripetal force? In this case, this is the friction offered by the road which acts as what it is. Exactly, this F centripetal is actually equal to the F gravitational. Again, here F centripetal is equal to the F, oh wait, what happened? Is equal to the F electrostatic, and here F centripetal is actually equal to the frictional force. Right, so that's the concept that the question is trying to evaluate here. Well, something that we need to discuss in circular motion. I just said it here because, if you are here for a question, make sure that you understand what the question is demanding. It's not demanding you for a solution, it's demanding whether you know the concept regarding the question. Okay, so next up is a question based on connected motion. Motion of pulleys. Okay, motion of connected bodies. So very good question. Two blocks A and B of masses 3m and m are respectively connected by a massless and inextensible string. The whole system is suspended by a massless spring as shown in, okay, so massless and inextensible string and massless spring. The magnitudes of acceleration of A and B immediately after, this phrase is really important here, immediately after the string is cut out. See, I don't have the diagram here, so those who have the handout, I think the diagram is labeled there. So give me a minute, I'll draw the necessary diagrams, then we'll go on to the solution. So now we have the initial condition. Okay. So what we'll do is we'll try to divide this question into the solution into three parts. One, before the cutting of the spring. Second, immediately after the cutting of the string. And the third one, what we'll do is we'll try to understand the comparison between impulsive and non-impulsive forces. So you may be wondering, why am I talking about that? As a third part, that will become more clear to you once we discuss the second part. So first part is before cutting the string. And what do we have here? The system is at rest, which means sigma fx and sigma fy will both be equal to 0, right? By Newton's second law of motion. Okay, now let us see the various forces acting along here. So we have the wall, the blocks, wall and the block. Immediately between them there is spring. A and B is connected via a string. I repeat, wall and A are connected by a spring. A and B are connected by a string, right? Right. Now let's see what happens here as a result of drawing the free body diagram of A. So what are the various forces acting on A? See, we know that if the net elongation is downwards, the restoring force or the spring force would be F is equal to Kx acting upwards. Okay, right. So that's it. Next up, we have weight of the body, which is acting downwards, right? So that would be 3m into g. And since there is a point of contact between A and B, repeat, since there is a point of contact between A and B, the string will be pulled towards B, and therefore tension would act away from this point of contact. We'll draw it one more time. So for the body A, there is spring force acting opposite direction, Kx. We have weight of the body acting downwards, which is 3m into g, right? And then what we also have is tension along the string along the string connecting A and B away from the point of contact. This is the point of contact. Away from the point of contact is acting tension. Now, if we apply sigma Fy is equal to 0 here, what do we get? What we get is T plus 3mg is equal to Kx. Now, what is sigma Fy? It simply means that sum of the forces acting in the vertical direction are equal, which means sum of the forces acting downwards will be equal to sum of the forces acting upwards. Now, since it is acting downwards, I have taken this as positive, and this is going upwards, I am taking Kx as negative. It transposes and becomes Kx. Okay, so that's there. Now let us see what happens with the string alone. So again, see, in the original picture, what is present here? The body A is present here, which means this body B will experience a tension away from the point of contact. This is the point of contact, and it will experience force away from the point of contact, and it will also have a weight acting downwards. So if you apply sigma Fy is equal to 0 here, what do you get? What you get is mg is equal to T, right? So this is important. It simply means that tension acting in the string is actually equal to the weight of the mass it is connected to it. Why is it important? Let's see. It is important because now, instead of this tension, what can you write here? You can bring this relationship here. And instead of tension, you can write here mg. So now mg plus 3mg is equal to Kx, and therefore 4mg is equal to Kx, which means the spring constant here can otherwise be written as 4mg. So we have a spring with a spring constant 4mg into x. X is equal to K is equal to 4mg. Right. Now let us see the case of after cutting the string. Okay. Now, one key word to understand this question is really important, which is cutting of the string immediately after. So we have immediately after cutting. That word is really important. Why is it important? That comes in part 3. So this is immediately after. Say for example, you were observing a t is equal to 1 second and then you are cutting a t is equal to 1.002 seconds. That is immediately after cutting. Okay, you're not observing this scenario after t is equal to 4 seconds. No, there's a difference. Okay, now what is the condition here? And the block A, the string is between A and B. When the string is cut, what happens is the primary effect. See, there is some tension between the points A and B. And when the string is cut, what happens with the tension? What happens with the tension is the tension becomes 0. Now, when the string is cut, the string is hanging without any tension. Or in other words, we can say that the tension is equal to 0. Right? The tension is equal to 0. Now, okay, give me a second. Yeah, now the tension is equal to 0. Similarly, for the body B, if you try to visualize this, this was the tension, the string here. The string would be now almost vertical, but without any tension. B here, the string was like this. There was some tension, but it will now fall down. And for B also, string is hanging without any tension, which means tension is 0 in the string for B as well, right? Now let us see. Excuse me. Now let us see how to solve the how to write the free body diagram. So free body diagram and how to apply Newton's second law of motion. So if we draw the free body diagram here for A, we know that spring is now under the restoration effect. Why? Because the string is cut. It was elongating. Now, well, if I have to draw this diagram correctly, the length of the spring should actually come down. Why should it come down? Because give me a second. Yeah, so this is how it should look like, right? Because the spring is now moving upwards. Okay. Now, since it is moving upwards, therefore the spring force will be acting kx. So yes, we have spring force acting kx. What other forces are acting? See, since it is a weight, definitely being a weight, which force will act? Weight will act. So we have not mg, it will have to be 3m into g, right? 3m into g. If you want, you can write down tension also for your clarity if you want it. Well, which is actually 0. Now, since the net direction of motion is towards the upward direction, all forces along the upward direction will be given as positive. Since kx is along the direction of motion, we will give kx as positive, and this will 3mg as negative. So if we were to write sigma fy is equal to, is it 0? No, there is some acceleration, so that will be m into a. What is sigma fy? Plus kx. Y plus kx, positive along the direction of motion. So we have plus, my bad, we have plus kx minus 3m into g. Oh wait, this is not ma, this is 3m into a. Will be equal to 3m into a, right? Okay, now what is kx from the previous derivation? Kx is actually equal to 4mg. We derived in the first part. Now we can write that 4mg minus 3mg is equal to 3ma, and therefore mg is equal to 3ma. M and m will cancel, so what we get is a is equal to g by 3. Therefore this body A will move up with a velocity with an acceleration of g by 3. Now let us see the case of B also. See, so what happens for B is, if you draw the free body diagram of P, earlier what was acting there? Tension was acting. That tension is now 0. So the only force acting on B is m into g. So if we were to write sigma fy is equal to m into a, what is sigma fy? Since B will come downwards, mg will be taken as positive. Mg minus t is equal to ma. The value of t is 0. So what you get is mg is equal to ma. And therefore what you get is m and m will cancel. What you get is g is a, which means this body is under free fall. Right? So the body is under free fall. Okay. Free fall. So we found out the value of a for the body A and for body B, which means let us go back to the answer now. Yeah, so the acceleration of A is g by 3 and acceleration of B is g, which means the correct option is okay, A is g by 3. Okay, there might be some problem with this. Okay, this is the correct option, g by 3 and g, right? Now let us see one more thing, which is a very important point when it comes to the discussion on impulsive and non-impulsive forces. You might be wondering why did I take that value as 0? So we'll just go through a very small explanation here. See, this is a wall which has a hanging portion like this. I have a spring here. Now, if I attach a mass here, right? If I attach a mass here, this mass will definitely extend the spring, right? This mass will definitely extend the spring. And when this mass will extend the spring, there will be some restoring force acting upon the spring, which is what we call as F is equal to kx. Now, there was a string here. The moment you cut the spring, this restoring force will come into picture and it will completely try to decompress the spring, and eventually it will come like this. But if this is at t is equal to 0, this is at t is equal to 1 second, and if you are cutting this at t is equal to 1.00, okay, let us say if you cut that at t is equal to 2 seconds, right? Now at t is equal to 2.00 seconds, or maybe say t is equal to 2.2 seconds, what happens is the spring won't come to its natural length originally. So see, this is the natural length, right? This is the natural length of the spring. It won't come to the natural length originally, original natural length very instantly. It will take some time. Maybe at t is equal to 4 seconds, the spring is back to the natural length. So since it takes some time for the spring to come back to the normal position, we call these kind of forces as these kind of forces as non-impulsive forces. Whereas when you discuss impulsive forces, say for example, this is the wall here. We have a block attached to a string which is hanging on the wall. If you cut the string, immediately what happens is, see, this block will definitely fall down, right? This block will fall down. And what will happen to the string? There was some tension acting in the string which is caused due to this mass, and that mass is not present now, which means the tension acting here will be equal to 0 instantly. And therefore tension is an impulsive force in this example. But what you should understand is tension can be both impulsive and non-impulsive as well. Something that we'll discuss much, not here. I wouldn't say that's really essential for the NEET aspirants. Maybe for the JEE means. But of course, if you have to understand the concept, please make sure you go through the theory given. Right. So that's it for this set of questions. Moving on to the next question.